with the welcome. So good morning, everyone. Very welcome to the biannual recent advances in viticulture and enology. Welcome back for those that actually joined us yesterday afternoon as well. I hope you found it to be a very informative day and interesting to see all the novel work that we are doing here at the department, and almost everything you could see the potential application in the industry, helping growers and producers to be more sustainable and hopefully improve the quality of your product as well. I would like to quickly thank both Karen Block and Caroline Furman. They're really the driving force behind these programs. I sit here and look pretty, but they do a lot of the background work, or we won't be able to get all these programs off the ground, because moi is very number 99 most of the time. And we would like to thank our extension partners. You'll see there's a slide popping up. Without their support, we won't be able to do most of the extension programs that we do, probably go down to like 1 or 2 programs a year. Based on the support we get from ANR. But, you know, Khan and myself are free. Our salaries are paid by the state. So we're very, very thankful for that. And actually talking about Khan, but before I move to Khan, I would also like to say a little bit of housekeeping. For those of you that weren't present or weren't attending yesterday, at the bottom, there is a Q&A button. If you have any questions for the speakers, please type in your question in the Q&A. If there's time, we will ask that question live and the speaker will answer it. If we do not get to the question, we ask the speakers to stay on after your presentation, and please answer that by typing it in. And if for some reason that isn't possible, we can copy and paste from there, send it by email, and we will send you an answer by email. Please do not use the chat function. We can't copy from the chat to the Q&A. The chat is for you to welcome or say hi or chat with a friend that you see online. That's your networking tool. But the Q&A, that's for asking questions to the presenters today. So thank you for everybody that's presenting this morning. We're going to start off with my counterpart, Khan Kurtrell. He is the UC Cooperative Extension Specialist in Viticulture, splitting his time between the department here at UC Davis, as well as our Oakville Experimental Station in Napa. So thank you, Khan. I'm going to hand it over to you.
All right, let me share my screen. Okay, good morning, everybody. So thank you for scheduling me. I'll be talking about same season and carryover effects of sourcing adjustments on Cabernet Sauvignon and how this will affect primary and secondary metabolites in grape and wine. So in the vineyard, we work with the canopy, trying to drive a crop load from this. The shoot system of the grapevine is made up of the stems, the leaves, and the clusters. So collectively, when we put them on a trellis, the length, height, width, leaf area, shoot density, and a leaf layer number will make up the microclimate of the grapevine. So this couple of cubic inches of volume is what we manipulate, and this is what affects the microclimate as the amount of leaf area and the distribution of this leaf area and the interaction with the above ground climate is what makes the end product in the end. The role of the canopy in the grapevine and in all plants is to fix carbon and to actually make sugar. So we reduce carbon dioxide in the leaves, which act as the source with the use of light to make photoassimilates, which are mainly sugars. And depending on the time of the year, These sugars may be put into the roots, or it can be put into the shoots, leaves, or more importantly, into the berries, which make up the clusters. So as you can see in the inset here, the speed of photosynthesis will increase linearly as you put more leaves in a system, such as a shoot system, and the ripening rate, the accumulation of bricks per day will increase. So in research settings, we can measure this using a photosynthesis meter, et cetera, so on and so forth. However, this may not be as practical for growers, to lug this stuff around in vineyards, as you very well know. As we move through these things, there's a lot of misconceptions. Exposure to solar radiation is not absolutely necessary to reach maximum skin anthocyanin in plants. As you look in the first inset, when we compared Cabernet Sauvignon and Petit Verdot, the x-axis canopy porosity, the y-axis is anthocyanins. As we increase the canopy porosity, we do reduce the amount of anthocyanins, that are, retained in the berry. And of course, if you pick green berries and grow them on petri dishes in complete darkness, as you increase the sugars to about like 16% in the solution, in the absence of light, the berries will turn dark. And of course, this was more highlighted with our research in our red blotch grapevines, as the total soluble solids increased in uninfected grapevines that did not have a red blotch. We were able to make the correct amount of sugars, to make the correct amount of anthocyanins. Conversely, when we had red blotch, we did not make enough sugars, therefore not enough anthocyanins. So there's almost, this relationship where, sugars will call for the biosynthesis of anthocyanins or secondary metabolites. So optimum light environment in the fruit zone during ripening, the goal has always been to optimize diffuse or indirect sunlight within the canopy interior. Yesterday, Dr. Torres alluded to this fact. As we expose the berries to more sunlight with shoot removal or shoot thinning or their combination, we were making more flavonols, and these are the only compounds that will respond in the berry skin to solar radiation. However, anthocyanins degraded very rapidly as we expose them to more sunlight, meaning that both the lack of carbohydrate biosynthesis and overexposure inhibited this. Photoassimilates travel within the plant. We have used this to our advantage for many, many years, especially in table grape production. We can girdle the plants to stop the flow of photoassimilates from the shoots to the roots and put them into the berry. This is a classic trial that Professor Williams did in Kearney with Thompson seedless grapevines. As he girdled the grapes after a fruit set, he was able to accumulate more photosynthetes or more carbohydrates per vine in the clusters and the leaves, as opposed to putting them into the roots later on into the season, therefore making berries. Of course, we do not girdle grapevines in wine grape production. What we do is we manipulate leaf area to fruit ratio, or the RAVE index, and these can be used interchangeably. This work was done at the Oakville station, summarized by Professor Cleaver and DeCruzlian back in the day. There's a linear relationship between the leaf area and crop weight, which is basically a source to sink ratio, to the crop weight to a pruning weight ratio of the vine, and then a leaf area to a crop weight ratio. Then you can draw a window here between 0.65 to 1.3 square meters of leaf area per unit of fruit, or more commonly referred to as the RAVE index between 5 to 10. So we say, this will be overcropped or undercropped if it's, outside. Of course, yields in grapevine is a very controversial topic. People say air. Of course, these photos are from the Oakville station. Leaving these $17,000 a ton of grape berries on the floor. When you come down to Bakersfield to Tehachapi Mountains area, the crop load window changes where the economic cutoff will be about 12 tons to the acre. Then this window will have to shift between 10 to 12. But it's not a static measure as you move towards different regions. So we set up this study to look at the effects of source and sink ratios on plant fitness, shifts in phenology, composition of the berry, and the wine composition. And we want to look at the effects on plant reserves on next year's carryover effects. Looked at the kinetics of ripening in the upcoming seasons, and then of course provide a science-based extension to California growers. Work was done at the Oakville station in a traditional vineyard planted to Cabernet Sauvignon on a 60-degree trellis. The vineyard was irrigated, 50% of crop ET replacement. It was a randomized complete block design with 4 blocks. It was a 3x3 factorial experiment. So the experimental design is, quite novel in our opinion. Most of the source sink relationships did not remove these confounding factors previously. What we did was we adjusted the vines to 22 shoots per vine in an 18-foot spacing, like a 3-vine panel. In this case, we either kept 100% of the leaves, 66% of the leaves, or 33% of the leaves. Also, on top of this, we kept 33% of the fruit, 66% of the fruit, or 100% of the fruit. So roughly about 45 clusters per vine was the max that we have seen. And this is how they look in the field as the treatments were applied. This is 33% of the fruit remaining, with 33% of the leaves remaining in the most extreme treatment. And this is the other most extreme treatment, 100% of the fruit remaining with 100% of the leaves remaining. And this is right at a BB size, berry size. When the canopies are mature, this is how they look like. So it looks, fairly, extreme in the most extreme treatment. However, this is not uncommon in the region where I have been working recently. This is what people call, naked leafing, and they strip the vines of the leaves to expose the berries or the clusters to solar radiation. Well, looking at the results, and this study ran for 3 years, what we found in the carbohydrate metabolism is that leaf area is what determines carbon fixation in the grapevine, not the amount of fruit that we retain. So in this case, what we're seeing here is that the net photosynthesis throughout the season. The most extreme treatments are plotted: 100% of the leaves, 100% of the fruit, 33% of the leaves with 100% of the fruit, vice versa. What we're seeing here is the treatments were applied, and then you can see that they immediately have an effect as they're going through. We see that as we have the least amount of leaves, photosynthesis goes into overdrive. It's trying to feed even the littlest amount of crop it has on there. The effect of crop load and effect of defoliation is separated in the smaller insets here. Effect of crop load is negligible. However, the effect of defoliation is the driving factor. If you have the correct amount of leaves on the vine, the leaves are working properly, they're not in overdrive. Also, to follow up on this, leaf area determines the plant water status as well, not the actual amount of fruit or the crop level or crop load that we retain on the vine. Again, as the stomates are open to exchange gas to fix carbon, they're also, doing the most of the water vapor exchange. Again, 33% of the leaves with 100% of the fruit, or 33% of the fruit is what's doing the most water vapor exchange case. When we look at the plant reserves, again, the plant reserves in this case was measured as the dynamic changes in our root starch throughout the season. So this is 3 years of root starch. This started soon after harvest was over in the initial year of the experiment. As you can see, there's not a whole lot of differences between treatments early. I mean, soon after harvest, the plants are making up reserves. When we do the treatment application soon after berry set, that's when they spread. As you can see, 33% of the leaves is not accumulating as much starch in the roots, and then they slowly creep up, and then get back up to where they need to be before the end of the year. Again, the amount of crop load on the vine has no bearing on the storage reserves, which was mainly measured as the root starch in this case. Leaf area is what determines it. When we look at yields, this is fairly straightforward. These are interaction graphs. The x-axis percent of the leaves. The columns are the number of fruit, or the percentage of fruit that we retain. 100% of the leaves with 100% of the fruit is of course going to have the most amount of yield, as you can expect. In the initial year of the study, they separate as we expect. However, when we come into the second year in 2018, we start seeing the carryover effects of the least amount of leaf area that we retained on these vines, as the plants are not able to mobilize as much starch as they would like to have to feed even the lowest amount of fruit that we retain. And this is more evident in the leaf area per plant in the following years of the experiment. Yield per plant, again, if I look at this from a leaf area to fruit mass in square meters per kg, I have drawn the lines here as undercropped or overcrop. As you can see, most of our treatments in this case were overcropped. Very few were undercropped, and the undercropped meaning 33% of the fruit, even with 100% of the leaves. And as the years go on by, the 33% of the leaves are treatment is going into an overcropping situation, even with the least amount of crop that we retain on them. And this will give you an idea of the linear trends. So the left-hand side of the slide is a leaf area to fruit ratio over the course of years. Leaf area to fruit ratio is more affected by our defoliation treatments. The right-hand side of the graph is a yield to pruning weight ratio, which is a RAVE index. This is more modulated by crop thinning or crop removal, but in each case, you see the linear trends carried to the quadratic level. The carryover effects we see are in the canopy leaf area, even though there was no treatments applied in 2019, they were just left to grow. When you look at the starch versus soluble carbohydrates in the roots, the bottom figure is the soluble carbohydrates. This would be the exchangeable units within the plant. These are what's affected by crop thinning, not necessarily by leaf area. However, in the end, after harvest, they do catch up very quickly. And the main effect then again being leaf area determination. So vine balance for photoassimilate partitioning, it's more of a practical measure, not necessarily a physiological measure. And it was not a one-to-one ratio, meaning that removing 5 units of clusters did not result in 5 units of benefit. RAVE index, or pruning to or yield to pruning weight ratio, it can give you a crop removal directive. Leaf area to fruit ratio, it's more of a photoassimilate partitioning directive in this case. When we look at the root growth, the adjustment of leaf area to fruit ratio misbalances, plants were dug up and then partitioned, and roots respond very similar manner as the shoots. So again, this is driven by the leaf area, not necessarily by the amount of crop we retain on them. It did not affect biomass partitioning. Leaf area determines biomass. When we look at cluster berry thinning, anthocyanin content, this is again driven by the amount of leaves on them. You see the linear trends as we retain less fruit or less leaves, we see less anthocyanin biosynthesis in the plant. And then this carries on year after year. Every year, as we remove leaves, we do not make enough anthocyanins because this is directly related to carbohydrate partitioning. This reverses in the tannin content as we look at it from a molecular mass increase. We do make more tannin in this case. However, this was coming more from seed tannin in this case, so it gives you a taste sensation rather than a tactile sensation. Vegetal flavors follow the grape berry kinetics. As we increased or as we made more sugar, we were able to degrade methoxypyrazines faster. If we did not have enough leaves, we were not able to make enough sugars, and that inhibited our ability to make or degrade methoxypyrazines in this case. Wine composition flavors follows everything we see. This is a graph where importance increases as you move towards red. 100% of the leaves, 100% of the fruit in our case, made the most balanced wine. When we look at the wine flavors, as I separate them into esters, ketones, etc., so on and so forth, or even fruit-forward aromas with the carotenoid degradation compounds such as damascenone, etc., so on and so forth, we see that crop thinning has a very strong effect, but extreme crop thinning, we do get less fruit-forward flavors. We also see a very strong effect of leaf removal on the wine flavors. We do get a very harsh alcohols, the C6 alcohols in this case. In the end, berry size is more sensitive to canopy size more than crop load or irrigation, as we found in our other studies. Canopy size dictates carbohydrate metabolism, thus the speed of ripening. Small canopies reduce plant reserves than overcropping. The challenge for maintaining yields is controlling big canopies early in the season. However, with these consistent droughts, that might not be as big of a problem as we had in the past. Vine balance is a valid concept. Some people are questioning, like, why do you still study this? This should not be questioned. It is a valid concept, but it's a practical concept. Crop removal or no crop removal does not affect the grapevine reserves in the hot climate. Defoliation is what reduces root growth, reserves, and subsequent yields. For example, avoiding pruning in September, too much leaf removal is not a good thing to make like a color, as people call it. It's not really a science based on hot climates. Crop removal has an undesirable effect on our wine flavor composition, more so than our plant fitness in the hot climate. Carbohydrate metabolism directly affects berry flavonoid and flavor precursors and thusly wine composition. So this is not driven by exposure in regions where we have more than 3,000 growing degree days. So our findings so far, this is how I would summarize this. You have to make a canopy size and a shape. That's a given. So with this, you're going to make photosynthesis and make sugar-induced growth. Once you have a plant-reduced carbon pool, you're going to have a berry enlargement and a sugar allocation. This is what determines berry size. Once you start getting into the ripening season, you're going to have the dilution of soluble solids and osmotic potential. But then again, canopy size and shape is what calls for the abscisic acid precursors, which will kickstart ripening, which is coming with soluble solids accumulation. Only after then, water deficits or crop load control looks like indirectly affecting other ripe grape traits such as flavonoid or volatile aromas and flavors. If we do not have enough leaf area, you have this inset here, as I'm showing. We have a spontaneous berry abortion because we do not have enough leaf area to feed this fruit that we retain on the vines. So with that, I'd like to thank everybody that funded this study, American Vineyard Foundation and Groth Vineyards and Winery, who are our neighbors in Oakville. Cameron and Mary made the wines. And of course, all the people, especially Johan, who worked on the study for 43 years. So with that, I'll yield. How do I?
Thank you, Khan. You used up all your time. So
Perfect.
there isn't time for questions, although I do see there is a question in the Q&A. So if you could please.
I'll answer them there.
Thank you very much. And there may be a few more starting. So next up, our next speaker is Andrew Waterhouse, well-known wine chemistry professor at the Department of Viticulture and Enology. And he's going to explain wine oxidation for us, a very, very complex issue. So I'm waiting for Andy's video to come on.
Can you hear me?
I can hear you, but I can't see you. Yeah, there we go. Okay, Andy, so if you share your screen, it's over to you.
Thank you, Anita. And thanks for inviting me to participate in RAVE this year. It's great to be here. I'll be talking about wine oxidation again. I've talked about it in the past quite a few times. And I want to acknowledge the fact that our students, Meow and T, have contributed to this details of this presentation. So oxidation is an old problem, perhaps the oldest. Was recognized by Pasteur, who basically said that oxidation makes the wine. And it certainly has a very, very large impact on wine. And in certain quarters in Burgundy, although they're starting to resolve this, premature oxidation has become an issue. And certainly for, I think most people who have been in the business for a while, they have had problems with wine oxidation. It doesn't happen, obviously, all the time, but there's always a wine here or there that has an oxidation issue. So a question that's been posed to me over the years is, how long will this wine last? And it would really be great if we had some way to measure that. Because it's an oxidation process, it's been presumed that antioxidant assays, so tests of antioxidant potential or what have you, should be able to do the job. I'm going to explain some of the basic chemistry of the assays and show how they work and show how they can relate, the information they give relates to oxidation of wine. And then I'm going to finish up with some proposals for alternate methods for measuring this or answering this question. It's a question we've been trying to get at for quite a few years, and I think we now have a new approach, perhaps, that will make a difference. So, how do these antioxidant assays work? In general, they challenge a wine to oxidation. So you add something that's an oxidant, and you look at how the wine responds. There's a number of, quite a few different assays. I'm going to talk about two that sort of are the two classes of assays. In one case, we use iron as an oxidant. In another case, another example, we actually add free radicals to the sample and look at free radical quenching. There's also in the market now, there's some cyclic voltammograms. Well, they don't call them that, but anyway, that's what they are, that essentially do an electrochemical assay on the sample and give a current that shows the amount of oxidation that can occur. And this is, again, gives you an idea of how much what are called reducing substances are present. So essentially, we're challenging the wine to oxidation, and the amount of reducing substances then resists that process. So it gives you an idea of perhaps, how much oxidation the wine could tolerate before it becomes oxidized. The cyclovoltammograms are interesting because they distinguish between different classes of materials based on how easy they are to oxidize. So for instance, ascorbic acid and SO2 usually give a separate signal that's easy to spot. At least it's somewhat separated from the phenolic compounds. So the first method I'm going to talk about is the DPPH method, which you add a reagent, which is essentially a free radical and has an absorbance that's easy to spot. So it's called DPPH, and down on the bottom I have a diagram, and that little dot on that end means it's a free radical. So you actually buy a reagent, which is a free radical. And then anything that's what's called a hydrogen donor will quench that free radical, and you'll lose the absorbance. So the way you do this assay is you make up a solution with this DPPH in it. You do a spectral measurement. You add your sample, and then you see how much of this absorbance, this light absorbance, is lost, and that tells you how much reducing materials or hydrogen donors you have in your sample. So the key thing here is that catechol groups. So I've drawn on the side there, the catechol group is a phenolic with two hydroxys adjacent to each other. So these are found in lots of phenolic compounds in grapes and wine. So for instance, tannins have lots of catechol groups. Even in white wine, the hydroxycinnamates, the most abundant one, caffeic acid, has a catechol group. So there's most of the phenolics present in wine contain this functional group, and so they're very good at quenching this free radical. The other class of materials are thiols. So things like glutathione and so on are very good at this. And there's a number of other thiols I'll mention later. So those are very good. They donate a hydrogen very easily, and they also quench this free radical. Sulfur dioxide is not so good, but it turns out it can participate through sort of a back door. So I'll show you that here. So when catechols react with DPPH, they go through a number of steps and quench the free radical. But at the end, the catechol is oxidized to a quinone, and that would be the end of it in terms of this, quenching the DPPH. But if you have SO2 present, the bisulfite form will reduce the quinone back to the catechol, and that will then be recycled. So if you have SO2 in your sample, then you get a larger response because the SO2 is acting to recycle things back to the reduced state. So you can get, so if you have SO2 in your sample, you can detect its presence in a wine sample because of this recycling feature. So catechols are which I said are really the good hydrogen donors and the primary substance that responds in this DPPH assay. And the catechol, as I mentioned, the sources of these are in red wine. Certainly the condensed tannin is a very good source of these catechol groups. Also in red wines, if you have some flavonols, there's some of that present. And then hydroxycinnamates are found in all wines. So the other thing that can act, so besides the SO2 is thiols, they act both as a hydrogen donor and as a quinone recycler. So those are very effective. So there's some interest in adding glutathione to wine as an antioxidant. And certainly the French are very interested in measuring this in wine to see how protected the wine is to oxidation. At least at this point right now, I don't think you can add glutathione to wine legally anywhere. The Kiwis were looking into, figuring out or adding it to their regulations, but it's fairly expensive. It is found, it's quite abundant in grape juice. It's usually broken down by the yeast during fermentation. And then sometimes you can have a little bit of it left over after fermentation. The other method that we use to measure, or the basis of an antioxidant assay, is called the FRAP assay. And by the way, the DPPH and the FRAP assay have been proposed by various people to be good ways of measuring oxidation potential of a wine. So the FRAP assay is fairly straightforward. You add iron 3 to the sample, and then the sample, if you have reducing species in the sample, then it reduces iron 3 to iron 2. And then you also have this complexing agent called TPTZ, which binds to the iron 2 very tightly and produces a darkly colored iron complex. And so you measure the amount of that iron complex, and it tells you how much reducing material is present in your wine. And it's called a ferric reducing method as a result of this chemistry. So in the FRAP assay, the catechols are very good at reducing iron 3 to iron 2. SO2 is also quite good. The thiols are a little bit weak. But again, as I showed earlier, if you make quinone through the assay, then the thiols can recycle it back. Fluoroglucinol can also do this. It's not clear how effective they are. They haven't been directly tested. The fluoroglucinol is the a part of the tannin that looks like fluoroglucinol from a chemical perspective. So tannin is very good as a reducing agent because of that group. It doesn't work that well in this particular assay, but it works well in the DPPH. So this just shows this recycling phenomenon. So if we have a catechol group like this, in this example here, we have caffeic acid reacts with iron 3 and produces iron 2, which is undetected. And if you have glutathione around or SO2, those recycle the quinone back. And so you get a bigger response in the assay if you have SO2 or thiols around in this assay. Okay, so now this is going to be on the quiz. This shows all the different reactions, the different pathway for wine oxidation. And the key thing here is that there's two primary products that are found in oxidation. One is the quinone, so various catechols that are present in tannin or hydroxycinnamates will get oxidized when oxidation is occurring. They'll produce quinone. The other product of that reaction step is hydrogen peroxide. Now, if you have SO2 around, the SO2 will quench the peroxide and also quench the quinone. So the SO2 here is a very good antioxidant because it disposes of the quinone that's formed in this first step. It'll also dispose of the peroxide. Now, if you don't have enough SO2 around, then the peroxide will go on in another step and ultimately produce aldehydes. So when you're doing micro-ox or deliberately oxidizing a wine, what you're trying to do is actually make aldehydes, because the aldehydes are important for color stabilization and so on. So, but if you have SO2 present, after you make those aldehydes, it'll also bind the aldehydes. So you can sort of hide the oxidation after the fact if you have enough SO2 around. But the key thing is that it's the quinones and the aldehydes that are really the products of oxidation that we can put our hand on, right? And so the key thing is, if we know what can dispose of the quinones and the aldehydes, then we can really look at what in wine is a good antioxidant, because it's quenching these products that's actually how antioxidants work in wine. So when we look in a little bit more detail, if we look at quinones, they react very well with thiols. So things like glutathione would be very good at getting rid of quinones. Ascorbic acid also is very, very effective. SO2 works great. And tannin also works great as well. It's a little bit slower, but you have lots of tannin in red wines. And that's one of the reasons that red wines are protected from oxidation, because when the quinones are formed, the large amount of tannin there actually scavenges the quinone before it does anything else. One of the problems with quinones is that it react with thiols. In some cases, we want that to happen if, for instance, their wine smells like rotten eggs. But many wines have 3-mercaptohexanol, which is a nice fruity aroma. And if you don't have much of that, then you can lose that fruity flavor by oxidation. And so that's one of the reasons you would add SO2 to your wine, is that to protect that flavor, the way it works is oxygen gets into the bottle or whatever, you form some quinone, that's unavoidable. And then instead of losing your grapefruity aroma, the SO2 scavenges the quinone and so on. So you don't lose the flavor. All right. Now, this slide's pretty messy, but it does show some of the reactions of acetaldehyde. And that's the other product of oxidation. So what could we use to measure or what would protect us from the presence of acetaldehyde? And again, we see some of the similar things. Glutathione is pretty good at scavenging acetaldehyde. SO2 is great. The flavonols or the tannin does react with acetaldehyde. Some of these reactions are reversible, and so things come back. So for instance, the ethanol reaction, the acetaldehyde does react with ethanol, but it comes back to acetaldehyde very easily, and same with glycerol. So some of these sort of hide some of the acetaldehyde, but don't really get rid of it completely. But at any rate, many of the antioxidants are similar. We have our SO2, anthocyanins, the tannin, glutathione. So what could we do to measure just those things? And that's the crux of this is the antioxidants here. That I have this inventory, thiols. And for phenolics, it's really not, most of the phenolics are not good antioxidants from the point of view of scavenging these oxidation products. It's the fluoroglucinol containing ones. So the tannin is very good, but for instance, hydroxycinnamates don't have that capacity. A lot of the anthocyanins don't react directly, or the anthocyanins don't have the catechol group, so they don't really fall in that category. But one of the problems is that many of these assays, the antioxidant assays that are out there, the FRAP assay, the DPPH, all give a very strong response from catechol-containing phenolics, which don't really protect the wine. So that's the problem with those assays, is that they're giving a very strong response to a functional group that doesn't really protect the wine against oxidation. The other good antioxidants are ascorbic acid, or SO2, of course, and as we'll see, amino acids, particularly the sulfur-containing ones. So in a way, those fall into the category of thiols. This just reiterates what I said. The current assays, antioxidant assays, measure a lot of the catechol groups. So they are measuring some of the antioxidants because of those reactions I was showing you earlier. But these essentially constitute a very large interference in the measurement we would like to do. So what we'd like to have is a method that does not measure the catechols, but measures reactions with either the quinones or aldehydes. So these are our two products that we're interested in tracking. So recently, there's a French group that published a report where, using a very sophisticated method, they measured what they call the antioxidant metabolome. So essentially what they're doing is they're measuring all those things that I just said, the thiols, ascorbic acid, etc., in a white wine system. And the way they do that is they take a wine sample and they add a reactive quinone, add it to the sample, and then they look for all the mass spec signals that they can tell are coming from the fragmentation of this quinone. So there's some fairly sophisticated mass spectral analysis going on that they're looking for specific fragmentation patterns. They're using that to identify what was formed when they added this quinone. And when they did this, they actually removed the SO2. So the SO2 is not, because otherwise, if they hadn't removed it, they would get quite a few. Most of the products would have come from the SO2 reaction. And what they find is that, at least in a white wine now, remember the white wine doesn't have any tannin. Many of the products, in fact, most of the products are coming from amino acids and peptides that contain cysteine, which is a thiol, very reactive to quinone. So not too surprising, except I think in the past, we've never really thought of amino acids and peptides as being a major contributor to the antioxidant potential of a wine. There have been specific statements that glutathione, which is one of these peptides, was very important. So many of you probably have heard of Denis Dubourdieu, who passed away a couple of years ago. He stated many times that glutathione content of a wine was very important to protecting it from oxidation. So this study essentially confirmed that, although with an expanded set of amino acids, that showed that these were the products that reacted with quinone. So unfortunately, that method is based on using essentially a $500,000 instrument and, of course, a couple of PhDs to keep it running. And the question is, can we come up with a new method that captures the reaction of all these antioxidants, or can measure reactions with quinones or aldehydes, and is simple and easy to run? And then we could use that to predict the oxidative capacity of wine. So this is where we are. This is our proposal is to work on this assay, and we'll be looking at that over the next few months to see if there's any potential there for an antioxidant assay. In theory, we have some ideas that we could develop into something that would be relatively simple to run. But of course, that's going to take a little while to work that out. And just want to conclude by thanking students who worked on this, and also our funding agencies, American Vineyard Foundation and ARCS Foundation, which supported T Nguyen during much of his work. ASCV provided some scholarships to some students over the years, and some other groups as well. So if we have a little time left, I don't know if we do, I'll be happy to try to answer your questions.
Yes, we do have a little time left. Thank you, Andy. One question in the Q&A. With glutathione abundant in grape juice, would use of mute or sweet reserve to sweeten a wine be of use in improving aging potential? Is an off-dry wine versus arrested fermentation?
Well, that's a very interesting idea. I hadn't thought of that, but it should, in fact, provide more antioxidant protection because of the presence of glutathione. The other source for that actually is in a yeast autolysis. So if you age your wine, barrel age your white wine after fermentation is done, the yeast that are present in the bottom of the barrel, if you're using a barrel, break down and actually re-release glutathione. So that's one of the reasons that barrel-aged wines are, let's say, better protected from oxidation, is because this process of aging on yeast lees sort of returns some of that glutathione back to the wine. And probably some other probably some other thiols as well. I know in the study that I cited earlier that was done in Burgundy, and presumably those wines did come from the standard barrel aging scenario.
Yeah. Well, thank you very much, Andy. We're almost back on time. Thanks to Andy. Thank you for a very interesting talk about oxidation, as always.
All right. Bye-bye.
Bye. Right next into our next speaker, which is Professor Elizabeth Forstall. She's our plant physiologist in the department. And thank you. I think you're sharing your screen and I can see it. Over to you, Beth.
Thank you, Anita. And thank you, Karen and Caroline, too, for organizing this great event and for all of you being here. So today I'm going to talk to you about a trial that I've had going on in the field for 2 years now. This year was slightly more complicated than the first, but it's to manipulate, what it is manipulating irrigation practices during extreme heat events. And so to give you a little bit of background in terms of the context of why I'm asking this question, both based on information from climatologists and from growers, is that we know things are getting warmer on average, and that the last 6 years had 5 of the warmest years on record. And in fact, 2020 was the warmest on record historically in the Northern Hemisphere, and tied with 2016 for being the warmest, depending on which measurements, but statistically identical to 2016. And so this is where you can see that temperature anomaly and really see that upshoot in the last 10 years. But more likely, it's not discernible, detecting that mean shift of a few degrees, but what is more discernible is the extremes. And so when you shift your average temperature over, what you often do is capture more extreme temperatures, and there's also feedback associated with that, so that we have more extreme climate events in general, and heat waves, which are 3 or more days above a certain threshold temperature, defined usually based on the place and the average temperatures over some baseline period. And so I'm sure you've all noticed this across California. On the left is just what we foresee being the number of increase in 3-day heat waves with the temperature above 100 degrees Fahrenheit or 38 degrees Celsius. That's a pretty classical definition for California for heat waves. CalAdapt defines it as such. And you can see there's going to be, over the next several decades, a pretty dramatic increase in the number of heat waves. And also what's really critical to note is there's also going to be an increase in potential evapotranspiration. So there's going to be increased soil drying and increased evaporative demand or atmospheric demand, and drying and pulling up of water through plants, which is really critical because that's also a really important aspect of cooling. So we use irrigation to promote cooling in canopies during these heat wave events. But we also know that heat stress needs to be mitigated in vines, and there are many means to do so, as it can affect wine and berry characteristics. It also can reduce carbon assimilation, stomatical conductance, which are all related. It can affect some of the biochemistry of the vine, affecting both photosynthesis, carbon assimilation, and causing oxidative damage and subsequent effects on berry chemistry, and can ultimately affect yield and other parameters that are relevant and have carryover effects through seasons. And so a study that I'm going to talk to you about today is based in Lodi, which is a region that has relatively high risk and concern for heat waves in the San Joaquin Valley. And it's really important to note that there's been noticeable increases over the last few decades in the average Tmax. And that's what we're interested in, is how much change there is in Tmax and how many days there are consecutively that have this. And so you can see this is from 1985 to 2015. been a pretty dramatic increase in average Tmax for the growing season. That's June, July, August, September, or part of the growing season. And there's also this increase in Tmin, which is actually increasing at a more rapid rate than Tmax, which is also a concern, nighttime temperatures warming, and this compression of the diurnal temperature range. And so just to focus in on Lodi, this is looking at days above that 38°C threshold. That's what will be used. That will be what we use to define heat waves in the context of Lodi, is that's above a certain range for, above a certain percentile for average Tmax. And the cutoff that we used was 38°C. And we considered a heat wave being 3 days or more, as I mentioned before. And you can see that in the next few decades, there's going to be a pretty dramatic increase during the growing season. This is largely during the growing season, and number of days that are going to be above this threshold, which will increase the length of heat waves, which we saw this past season in 2020, and also the number of heat waves. And really, duration of heat wave and timing is absolutely critical for some of the decisions that we make in the vineyard. And so this little dot here is the location of the vineyard. But before I dive into some of the actual methods for the experimental trial, I want to report some results of a survey that went out to many growers in the summer of 2020, because I think this is really relevant to understanding why it's really important to understand irrigation dynamics, not solely across the whole season, hitting a target ET or whatever your means of irrigating would be to soil moisture or ET or other parameters, but also that these decisions about how to irrigate before heat wave events are absolutely critical. And so just briefly, there were 60 wine grape growers or winemakers who were primarily responsible for the growing and the vineyard management. They responded across regions in California, North Coast, Sierra Foothills, Central Valley, Southern California, Lake County, Northern California. And they ranged in managed acres from less than 50 to over 500. So there was quite the range there. And not surprisingly, Cabernet was 40% of what the primary cultivar was, followed by Syrah, Petit Syrah, and then there were many others. Not too many Chardonnay in this, which I was slightly surprised by. So as far as what growers are concerned about, we surveyed on a scale of 0 to 4, 0 being not a problem at all, 4 being devastating, several climate and weather related issues, thinking about reduced precipitation, changing in precipitation, associated increased disease and pest pressure. This is something we're writing up now and we'll be sharing with industry soon. So you can look at the exhaustive list soon. But what we found is that drought and extreme temperatures, so water availability and temperature extremes, were the most concerning climate-related issues for vineyards. I think that would change slightly after this year's fires, as smoke was one of them, also a concern in certain regions, of course. And 47% of respondents considered it to be serious to devastating, which is pretty striking. So this is definitely a concern. And over 80% of, well, I actually didn't put the percentage in here, but over 50% thought that water application was a moderate to effective means of mitigating heat wave impacts. And then those who increased irrigation, over 80% of them increased it at temperatures greater than 100 Fahrenheit. So that threshold of 38°C. And the timing of water application of these people that increased, or these growers that increased irrigation, was 77% applied it before the event, and 21 during, if it occurred during veraison, and 66% before at harvest, and a similar amount at harvest, although fewer people would increase irrigation at harvest and base that decision on the ripeness of their grapes. So I think as a whole, this suggests that this is a really important consideration, and there isn't total comfort in what decisions to make. And so the goal of this study was to assess how changing irrigation application using a variable rate drip irrigation system could affect berry chemistry and plant physiology, within and across seasons. And so the study is taking place in Borden Hills, as I mentioned, in Lodi. It's in collaboration with Ian J. Gallo. It's Cabernet Sauvignon on 1103P. It's high wire, mechanized pruning. And the irrigation treatments were at 30 by 30 meter square pixels. I'll refer to them as pixels. And in the first year, in 2019, we used the treatments. We applied the treatment at the pixel basis. So our treatment was at 30 by 30 meter squares, or 30 by 30 meter squared units. And we had 3 treatments. We had one where we maintained 60% ET, the baseline. And then we had a treatment where we increased the irrigation by 2 times and 3 times, 1 to 2 days prior to and during the heat wave. So we were only increasing irrigation prior to the heat wave and during the heat wave, or the first few days of the heat wave. And so in 2019, as I said, we restricted our treatments to that 30 by 30 meter pixel. And 2019, while it wasn't by any means a mild year, it was much more mild than this past year. And we only saw 2 heat wave events, and one which was just before 50% veraison, and one prior to harvest, a few weeks before harvest. Whereas this year, and I should mention, as this will become relevant later, that we altered our treatments to capture 60 by 60 meter pixels. And the reason for that was that we could incorporate a remote sensing data. So we can actually look at using OpenET and other such projects, or Sentinel data or Avarice data, and look at spectral responses to altering these precipitation regimes. And that's why we increased it, because the signature of irrigation around our treatment pixels swamped out that signature in the first year. And this year ended up being quite challenging and intense for many reasons, as you all know. We did have 4 heat waves, one as early as May during flowering, and then we had 3 more, 1 pre-veraison, and then 2 post-veraison, and 1 right before harvest in September. And I should say that the overall amount of applied irrigation increased by 50% because of this increase in heat waves, and also increase in VPD, although that was moderated a bit by the smoke later on in the season. And I should say too, we couldn't do all of the remote sensing, linking to the remote sensing that we wanted to because of the impacts of smoke, but we plan to in the next year. So I want to summarize some of the results from 2019 first, and then move into 2020 and compare them. Again, we had these 2 heat wave events. And here you can see the irrigation treatments. The baseline was the target of 60% ET, 2 times that and 3 times that. I recognize that this seems like a lot of water application, and it isn't necessarily practical in all contexts for growers to apply that much, especially across a whole field. But I should also say that this was well within the range of what was applied in terms of decision making outside of our treatments. So it wasn't outside the realm of possibility in warmer regions. So just to show you quickly, we did see, while there wasn't very, very extreme stress signatures, we did see a reduction in mid-stem water potential post heat wave in both cases, and then a fairly rapid recovery. Similarly, we saw an impact on net photosynthesis during the heat waves. This is just an example from the second heat wave. You can see there's increased leaf temperatures and a reduction in net photosynthesis across the range of leaf temperatures. This is across diurnal sampling during the day, and then a reduction in stomatal conductance as well, which really explains a lot of the reduction in net photosynthesis. There were significant effects on yield. Again, not particularly surprising, but still only increasing irrigation for those few days and those 2 heat waves did have a fairly dramatic effect on yield, and the baseline having the lowest yield. Additionally, the baseline treatment where irrigation wasn't increased, there was higher bricks, and no difference in bricks between the 2 times and 3 times. there was higher pH. We started seeing separation between the 2X and 3X, and actually see a negative effect of the 3X treatment in some of the berry chemistry for 2019. And then we have lower acidity for the vines that were more stressed and didn't receive supplemental irrigation. We also saw a reduction in total anthocyanins as an impact of the 3X irrigation, and more pronounced reduction in anthocyanins in the baseline treatment. And we also importantly found that there was a decoupling of anthocyanins and sugars. This is something that Sadras and Moran and others in Australia have seen in experimental trials, but not in a field trial such as this. And we found the same thing, and where you had a higher Brix, and so you'd reach a higher Brix at a lower anthocyanins, and you see that decoupling, suggesting that if you're targeting certain phenolic compounds for your harvest, that as these heat waves increase and as you decide, depending on your irrigation regime, that you might not see the same relationship between anthocyanins and sugars as one would expect. I'm not going to go into much detail here for the sake of time, but we also saw consistent decline in malvidins and monomeric anthocyanins, really relevant to color. And that was consistent this year as well. And interestingly, we also found an effect of that heat wave 1 on tannins that persisted throughout the season, a reduction in tannins, both in the baseline and in the 2X irrigation treatment. And while we don't have all the wine chemistry data yet, and we don't have all of the sensory data or any of the sensory data yet, we are seeing some indications that treatments vary in wine chemistry. And we have tasted all the wines, both from 2019 and 2020. And we collectively believe there's a discernible difference, but we've yet to do the sensory studies due to COVID constraints, but that should be happening as soon as those relax, as they're beginning to do so. And so we look forward to that, being able to carry this all the way through the winemaking. And so I am now going to bring you into the 2020 season, which had many caveats, and there was a lot going on. And so having that many heat waves, and especially the aim being to set up a lot of equipment in the field for monitoring and sensors, was not something that we could do until later. So I'm going to present the data we have based on our field sampling campaigns, and then talk to you about some of what we collected for a period last year in terms of berry temperature and radiation, IRT, canopy temperature, and how that will play a role in this field season. So again, we had these irrigation treatments where we did the 2X and 3X before and during heat waves, with a few minor adjustments where we didn't catch the heat wave. And we also did more berry sampling. So we started sampling much earlier to capture tannin synthesis. So we did 12 time points of berry sampling this year. And it was not trivial to go out there, other than the fact that row spacing aided in our ability to maintain distance, but we had a really great team to do so. And Martina Galliano, the master's student on this project, was absolutely critical and essential in working on this and devising aspects of this project for both 2019 and 2020. She's now back in Mendoza, but I'm trying to get her back to do a PhD, so we shall see. So as far as physiological responses, I was rather surprised, but I suppose in retrospect, knowing that there was more water in the soil column, that there was no effect of the heat wave 1, 2, and very little effect of heat wave 3 throughout the beginning of the season. And so there was more water available in the soil at that time, and it really indicated that before you make these decisions about adding application of water, that you want to know what your water availability is. And so we're also adding in, we did have some soil moisture sensors in there, but not across all of the treatments, but we're going to take that into account too. But it's important to note that across 3 of the heat waves, even the one in August, there was very little impact, and not until impact on stem water potential. And not until heat wave 3 did you really see a difference between net photosynthesis. And so interestingly, you didn't really detect for heat wave 3 the difference in terms of soil water potential or leaf water potential too, but it did have a pretty dramatic impact, that not adding on that water in late August. And similarly in September, but again, you always seem to have this recovery. And again, in stomatal conductance, you see a similar trend, is that you have this pretty dramatic decrease in stomatal conductance in response to the heat waves where you do not add irrigation. But there wasn't a dramatic response or difference between the 2x and 3x. So, and as far as yield, there was a reduction in yield for this year as well, and a reduction in anthocyanins again, but it was almost as if there was this transiency in some of the changes in anthocyanins. And in tannins, we did see, interestingly, without seeing any physiological response, a change. And this is where we would want to have more canopy and berry temperature data during this part of the season to understand this and actually do some molecular work as well, is there was a reduction in tannin post heat wave 2 and post the majority of the synthesis of tannin, but then there was almost a recovery, and only at the end do we see a slightly significant difference. So we're interested in looking more into that as well, and we're still working on some of the berry chemistry from this past year. Again, we saw this decoupling as far as anthocyanins, or not anthocyanins and tannins, but total soluble solids and anthocyanins. In the previous year, or this is just a fitting of non-quadratic, and this is a better fit. It's a better model fit here. So there's actually an eventual, once you got up to these high levels of Brix, which is not too surprising, you saw this degradation, likely degradation of anthocyanins. And so it's this curvilinear fit. And if we compare results across the 2 seasons, again, this is in response to no increase in irrigation prior to and during a heat wave. You saw that there was an increase in total soluble solids in both years, an increase in pH both years, decrease in TA, so decrease in acidity, not surprisingly, in both years, and then a decrease in anthocyanins and tannins, and decrease in anthocyanins for 2020. So you do, it's promising that you do see these consistent effects as far as relationship between anthocyanins and soluble solids, as well as yield and other parameters. And we're processing the flavonols and the harvest time points now to look at other chemistry and other monomeric anthocyanins. So now that we have these data from the past 2 seasons, we're working on incorporating the berry temperature, canopy temperature, and other aspects. And ideally, well, we do now have set up our monitoring stations so that we can actually in real time monitor ET throughout the season and make more refined decisions. And now that we know there's that negative effect of too much water application beforehand, that 3x or negligible effect between 2x, or negligible difference between 2x and 3x, we'll probably hone in on actually assessing based on the current ET in real time, not just an estimate from NDVI, and then also incorporate more incorporation of remotely sensed data and soil water content so that we can assess how much of a reduction in berry temperature and resulting berry biochemistry changes there are. And then also one thing that will be really critical to relate is the VPD and canopy temperature relationship and how that affects berry temperature, leaf temperature, and berry chemistry, because we know that atmospheric drying has a pretty dramatic effect on plant physiology and biochemistry as well. And so lastly, we also have a project with a postdoc in the lab and Andrew McElrone's lab working, Nico Raab, working on using some of the GRAPE data, so the GRAPE remote sensing atmospheric profile and evapotranspiration experiment that Andrew McElrone spoke of, and using any energy balance approaches to assess physiological thresholds and appropriate water application in sites across California that have variation in Tmax distributions and VPD. And so that will be something he'll hopefully present to you in the future. And so with that, I would like to acknowledge all of our collaborators, especially the USDA and within UC Davis and Ian J. Gallo, my lab members, and the funding and support for this. I'll be happy to take questions.
Thank you, Beth. We're actually out of time.
Yep.
You used just on the spot 25 minutes, so well done. There isn't currently any questions in the Q&A, which I see a sign is explaining very well. We're having something really complex and nobody knows what to ask. I think I look at this project and I always see, like you say, the more you measure, the more you realize you have to measure. And at the end, when you measure basically everything known to man, it's going to form a very, very interesting picture. If you can hang on a little bit during, I see a question just came up in the Q&A. Can you hang on a little bit during the break and answer some questions by typing in the answers? That would be great. Thank you very much. Because it's actually now time for break. And I do want people a break that needs to go to the restroom like I need to. That's oversharing probably. But can you all please be back by 10:25? Because 10:25, Andy Welker is going to lead off the flash talks, which is always a lot of fun, and you do not want to miss out on that. Okay, thank you. See you in a few minutes, 6 minutes to be exact.
Hi, Karen, can you hear me?
Yes,
Yes, waiting for the clock to go to 2025 is a little bit less than a minute.
Yep.
I can go to the next slide here.
Are all the speakers online right now?
So actually, I can't check while I'm sharing my screen.
I can see 1, 2, 3, 4, 5, 6. Yes,
Perfect.
yes, everybody's online. That's going to give a.
Can I see them? How come I can't see them?
Pull up your participants
Okay.
and then
Actually,
you'll
we are
see.
missing one of them. I just texted her. She's the last one though, so.
Oh, good.
Oh. Oh yeah, I just saw. Yeah, she's missing. That's true.
She's Argentinian, so we expect that.
Well, it is 10:25, so I want to keep us on time. So it is time to kick off the Flash Talks and introduce our Flash Talk moderator, which is Professor Andy Walker from the Department of Viticulture and Enology. And I see Andy as the guru of Flash Talks, as he, for several years, moderated the Flash Talks at the ACV conference. And I thought it always was a great event to attend, a lot of fun. You know, especially in the beginning years when most of the students try to fit in a 10-minute talk within 3 minutes. And I can tell you, Andy, yesterday when I had to moderate the Flash Talks, I totally copied you. What did they say? Imitation is the sincerest form of flattery. So I got that old car horn thing that you use, and I tried my best to get my phone to be obnoxious through my microphone. It was not as good as doing it in person, but you know, second best. Anyway, so now I'm going to hand it over to Andy so that he can take off the Flash Talks.
Very good. Thanks, Nita. Yeah, this is always a fun event because 3 minutes is not very long.
It's on the same street. He's like 5 houses away.
Someone else on there too?
There
There we go. And my job is to not really moderate per se, it's just to be the timekeeper. And 3 minutes, you're going to get the bang, you're finished. And it's say no more at that point, and move on to the next speaker. I think there'll probably be room for questions and answers in the Q&A session, but we'll worry about that later. So with that, then I'm going to introduce the first speaker. That's Chris Chen, and he's going to take it away, give you his title and what he's up to. Thanks.
Okay, thanks, Andy. Hi, my name's Chris Chen. I am a PhD student in Dr. Walker's lab, and I focus on chloride tolerance in grapevine rootstocks. My title, pictured here, is the chloride tolerance in Vitis species varies continuously by deposition into above ground tissues and not by accumulation in roots. So let me get into it. Thank you for changing the slide. So why is salt a problem in grapevines? It's a huge problem and it's getting worse. We're having issues with drought, with climate change in general, and that causes salt buildup in different vineyard soils for a lot of reasons. I don't have time to talk about all of them, but so much so that, you know, Australian food code states that a wine must not contain more than 1,000 milligrams of soluble chloride. So it's that big of a problem. We did a study on this, on salt tolerance in grapevine rootstocks by crossing 2 different varieties, GRN 3, which was developed by Walker Lab at UC Davis in 2008 as a nematode-resistant rootstock. It is very susceptible to salt, specifically chloride, and we crossed it with a wild type Vitis aerifolia 9018, which has been shown to be very highly resistant to salt, and this is collected between the Oklahoma-Texas border. So next slide, please. Our results were interesting. We saw a huge variability in chloride accumulation in root tissues and much less variability in leaf and petiole tissues when you look at individual selections from this cross. But if you compare among all of the crosses, we saw that there was no real variation in this population in root tissue chloride accumulation. but continuous variation or continuous change or accumulation levels of chloride in the leaf and petiole tissue. And that's really interesting result. Also, the general fact that the roots take up a lot more chloride than end up in the photosynthetic tissues. So next slide, please. All right, just quick conclusions on this. So from our results, we can assume, or we have a hint that tolerance to chloride in grapevine rootstocks, especially in our individual Phytosacer folia 9018, is likely influenced by multiple genes because of the continuous variation we saw, and it can be inherited by their offspring. This is good news because it means that we could possibly establish breeding programs to introduce this chloride tolerance into grapevine rootstocks, and also that the variability in roots is much higher than in leaf tissues when you're looking at individual ones. I'm out of time, so I'd like to thank the California Grapevine Rootstock Improvement Commission for funding this, and Andy for supporting me.
Perfect.
Great.
Thanks, Chris. And the thing, my bell is ringing, but it's not ringing very loud, so maybe I'll just have to shout at 3 minutes. Okay, thanks, Chris, and we'll go on to Kim. Kim Marinelli is next, and she's going to give you some indication what she's up to as well. Take it away.
Hey everyone, Kim Marinelli. I'm a member of the Montpetit and Brenenbaum lab. And my research has been investigating the effects of oxygenation on redox potential, often referred to as ORP, in fermentation kinetics. So the goal of this research has been to explore questions like how is oxygen introduction at various times and amounts during fermentation altering redox status, and ultimately how is it linked to fermentation outcomes. Next slide. So generally my experimental setup has involved 6 ferments carried out in 1 liter bioreactors. I've been using white juice concentrate as a medium, and I've been running these ferments at 23 degrees Celsius and using EC 111 as my yeast. We've been measuring redox using Hamilton redox probes, and for redox control, I've been holding my ferments at a negative 60 millivolt set point. You'll see the experimental design for the data you'll see today, where we used oxygen via aeration to control redox. So control is accomplished by pulsing in air as needed to maintain the set point. In this experiment, redox control was shut off across the ferments in 16-hour increments. Next slide. So this figure depicts fermentation with no redox control, where the solid line is redox potential and the dotted line is the Brix curve. So we know that as fermentation begins and yeast metabolism accelerates, redox potentials tend to move towards more negative values. So as seen in this figure, redox minimum tends to fall somewhere between negative 100 and negative 200 millivolts. So the following figures you're going to see will depict fermentations where redox was controlled at 16 hours, next slide, 32 hours, next slide, 48 hours, next slide, 64 hours, next slide, and 80 hours, next slide. When you compared the uncontrolled ferments to the ferments that were under redox control, the longest, this demonstrated a 20% acceleration in fermentation completeness. So as you can see, the length of redox control correlated with fermentation completeness. We also have started preliminary organic acid analysis, which has demonstrated a greater acetic acid accumulation when redox was left uncontrolled. Next slide. And lastly, just as some supported data, accelerated fermentations were correlated with higher cell densities. Next slide. So I'm just going to leave you with some future work here because I think I'm running out of time. But here are some things we're hoping to explore further with this research.
And that's it. Just on the second. Okay, very good. You guys can read through those comments. Let me just cancel this thing here. It has a mind of its own, which is not unusual. Okay, so our next speaker is Christina Medina Plaza, and she's going to speak with you right about now. Go.
Good morning, everyone. I'm a postdoctoral researcher in the Overholser lab, and I would like to share with you the project I've been working on for the past 18 months, investigating the impact of storage conditions on rosé wine, particularly light exposure, temperature, and bottle color. Next. So for that purpose, I made 4 rosé wines in 2019 at UC Davis Winery out of Barbera, Pinot Noir, Grenache, and Zinfandel. The wines had different color, different residual sugar, alcohol levels, among other characteristics. So we could also study the impact of those as well. Wines were bottled in clear and dark green bottles, Bordeaux style under screw cap, and they were stored under LED, fluorescent light, or in the darkness at 15C and 20C. So that gave us a total factorial design of total conditions per wine. Then those were analyzed at bottling after 3 months and after 6 months of storage. Next. So all the differences that you're gonna see on this slide and all the results were detectable after 3 months and more noticeable after 6. So when comparing the color of the wine at bottling versus 6 months, we found a decrease on the color intensity and on the red component, and an increase on the yellow, potentially due to the oxidation of the wine. Regarding phenolic composition, we analyzed it by reverse phase HPLC, and we saw a decrease on monomeric flavonoids and anthocyanins, while polymeric phenols and pigments increased. That could also explain the differences we found and the decrease we found on the red percentage of the wine. The aroma profile was analyzed by GCMS, and we found a decrease on the esters and the long chain alcohols, pointing to a decrease on the fruitiness and the freshness of the wine. On the basic chemical analysis, we analyzed percentage of alcohol, residual sugar, acetic acid, and the only parameter that we found differences on was a decrease on free and total SO2. Currently, we're analyzing the reductive compounds by GCMS, and the sensory is being done in collaboration with Oregon State University. So unfortunately, I cannot give you insight on that. The wines that showed the largest negative impact were the ones that were stored in clear bottles under fluorescent light at room temperature, contrary to the ones stored in the darkness at solar temperature, independent of the color of the bottle, that saw a very small impact. Next. Lastly, I would like to thank the Overholser Lab and the UC Davis Winery for all their help, and the Leon Cisneros Research Fund for their funding support on this project. Thank you.
Perfect, good timing, right on the spot. Cancel. Okay, next up is Rincy Yu, or Cliff, as we know him well. He's going to give you his quick talk right now. Take it away.
Okay, thank you, Andy. Hello, everyone. This is Cliff from Colorado's lab at Oakville Station. Today, I'm going to present one of our recent publications titled as Soil Apparent Electrical Conductivity and Mass Carbon Isotopic Ratio Provide Indication of Plant Water Status in Wine-Grade Vineyards. Next slide. Let's start with some background of this study. Researchers are trying to find out new approaches to assess plant water status spatially, especially in the big commercial vineyards. And electromagnetic induction, EMI sensing, and carbon isotopic C13 analysis are the 2 approaches that people have been focusing on because they're not destructive to the grapevines and also can save labor and time. However, there are 2 issues that are still present to put these 2 approaches into the real production settings. One is, since the apparent electrical conductivity, ECA, assessed by EMI sensing is an integrated parameter, and what is being measured by this approach was not thoroughly clarified so far. Also, for C13 analysis, there was no sufficient evidence to show its relationships with grapevine physiology in hot or warm climate like California. Therefore, the goal of this study was to solve these 2 issues. Next. So dive into our results. We found out that the soil water content contributed the most significantly to soil ECA, followed by soil texture, including soil silt and clay, and soil salinity had the least contribution towards soil ECA. Next. Also, we noticed that the deep soil ECA was closely related to stem water potential and leaf stomata conductance. C13 analysis was closely related to season-long stem water potential, net carbon assimilation rate, and also stomata conductance. Next slide. So to conclude, we found out that soil ECA measured by EMI sensing, the deep soil layer can be closely related to plant water status. And also we found out that the soil water content and soil texture were the main factors determining soil ECA. In addition, C13 can be related to plant physiology in semi-arid viticulture regions like California with micro irrigation system. It is not only limited to cool climate and rain-fed production system. Next slide. This study was already published in Precision Agriculture earlier this year, so there will be more details, including about the study in that paper. The paper is open source, so all of you can check it out free of charge. And also, I want to thank everybody in my lab because they're awesome, and thank you for your attention.
Great.
That's it.
Thanks, Cliff.
Thank you.
Okay, he even finished on time and early, so he's setting a new standard. Next speaker is Ryan Sanfield, and he's going to start right now.
Hi, the title of my talk is called Sugar Output to Grapes is Sustained During Drought with Phloem Loading Regulation. Next slide. So this model simulates sugar flow in a leaf. It's transported through the vine and into grapes. And the purpose for this is, although we know a lot about how drought impacts photosynthesis and impacts grape yields, we know comparatively little about how it impacts the phloem vascular tissue in terms of sucrose output. So this mathematical model that was generated was compartmentalized into 3 sections: a source area, a vascular area of phloem and xylem, and a sink grape area. And we put different input parameters such as stomatal control, sucrose loading rates, resistivity of the phloem conduit, and different soil water potentials. And the output of the model was the amount of sucrose that was unloaded into the grape. And we wanted to determine how this sucrose export was impacted under different drought scenarios. Next slide. And so the results, panel A on the y-axis shows the amount of sucrose unloaded into the grape. Over the x-axis, different soil water potentials. As you go to the right, things get drier. The different lines represent different phloem resistivities. So as the soil gets drier, most of the time sucrose output isn't impacted unless the resistivity of the phloem is too great and under too much drought. The reason for the sucrose to plummet to almost 0 under different resistivity circumstances is because the viscosity, as shown in panel B, starts to increase exponentially under drier soil conditions. To remediate this, the right panel shows that if the sucrose loading transporters are regulated such that they shut off at high trigger pressures within the phloem, sucrose export to the grape is maintained over a range of water potentials and phloem architectures. Next slide. So the key findings of this study is that if the phloem resistance is too high or if the soil is too dry, this results in phloem failure. However, if the sucrose loading proteins within the phloem are regulated, this prevents this effect from happening, and this opens up the phloem to maintain transport under a wide variety of conditions. And so this result, importantly, we find it decouples the plant's water status with its ability to translocate sugar and allocate sugars around the plant. With that, I'd like to acknowledge my mentor, Megan Bartlett, and the Rossi and Catherine Esau postdoctoral fellowships. Thank you.
Great. Thanks very much. Thanks very much, Ryan. And our next speaker is Cecilia Guerrero. There she is, ready to roll. Take it away, Cecilia.
Yeah, Andy. Next, please. Next, please. Last year, the Nobel Prize in Chemistry was awarded to Jennifer Doudna and Emmanuel Charpentier for their contribution to gene editing using the CRISPR-9-Cas system. The beauty of this system is its simplicity. It has only 2 components, a guide RNA and the Cas9 enzyme here in blue that works as molecular scissors that cut the DNA at the predetermined site, defined by a short sequence in the guide RNA here in yellow. And most of the times, a mutation is created with this break is repair. And this mutation will turn off the gene. Next, please. At the Walker Lab, we have a protocol in place to deliver the CRISPR system into Chardonnay cells, and we chose the aquaporin PIP2-1 gene as a proof of concept because of its links to water uptake and because it can be examined at the vegetative state. We are working in collaboration with Millie Rom from Anne Britt's lab, who designed the construct. Here in yellow and orange, you can see the target sequences, and we introduce it into Chardonnay. Next, please. Next. Thank you. The regenerated plants are now in the greenhouse. We have confirmed mutations in several lines, especially with guide 92, as you can see in the table, and also find that PIP2-1 expression levels have been reduced in comparison with the control, the gray line, gray bar number 2, that is the control. And probably the transcripts are not functional. But the important thing is to analyze the impact of turning off this gene on the physiology of the plant. And this is now being done by the people from Macaron and Bartlett's labs, who are looking at gas exchange, water status, immunolocalization, and other measurements. In the bottom right, I am showing Mina Momayesi preliminary results, and you can see that the mesophyll conductance has been reduced in mutated line 15. Again, line 2 is the control. This has happened in well water plants, but not in dehydrated plants that are the bars in orange. Next, please. So today I wanted to show the CRISPR system working in grapes using the simplest application, but the potential is incredible. It is not only possible to turn off genes, for example, disease susceptibility genes, but also to introduce precise modifications that can alter multiple genes and their expression. And very important, the system is being optimized to produce plants free of foreign DNA, so that these plants will be considered no GMOs. Thank you. And last one is the thankful. Thank you to the Walker Lab and all our funding agencies. Thank you so much, Andy.
Thanks, Cecilia. Okay, that's it. Back to you, Karen.
I'm here. I don't know where Karen. Oh, there's
I'm
Karen.
there. I had
So
to stop
Karen,
sharing and then.
So Karen is going to be the moderator for the rest of the session. So Karen Block, Dr. Karen Block is the Director of Industry Relations, and she started just like 6 months after I started in the department in 2011. And so I hand it over to you, Karen.
So Anita, we're a little bit early. Ben's talk is supposed to start at 11. Okay. So should we take a short break?
Are there questions for the flash talks?
Actually, it looks like there are a couple.
Maybe
yes, so there's a question for Cecilia. So there's a question about for Cecilia about, can you still call the new vine Chardonnay?
Yeah. Well, you will change. I don't know.
No, the answer is it depends.
Yeah, we are not there yet to patent anything, and but for sure there are mushrooms that have been being commercialized with this. They have been modified with this technique, and they are not called GMOs. That's the scary thing, right? Maybe you can call it Chardonnay minus PIP2. I don't know. But you can you can avoid to call them GMO. That is what scares people, I think, the most thing.
Okay. And somebody else question about Nicarab. So Nicarab was set to do a flash talk today, but he had to withdraw due to research activities. So we didn't forget about Nico. Nico just couldn't take part today anymore. So that's the right reason you did not see him do his flash talk. Is Ben ready? Because that will just gives us a little bit of, he's not here yet?
I don't think he's here. He's probably, so just so people know, we're also in the process of hiring a new grape breeder. And so that person is actually giving a talk, I believe, currently. So he might be at that.
Yeah, it's question and answer time right now, so.
Okay.
Oh, Ben just came online.
All right.
Ben, if you can hear me, we're a little bit early and it would be great if you're ready to start.
Sure. I was just watching a recruitment seminar on grape breeding, but yeah, I saw the email that we're ahead of schedule a little bit, so I can definitely jump in.
Thank you. Well, I'm going to shut up now because it's supposed to be Karen that's the moderator.
All right. So Ben, as soon as you're already on it, sharing your screen.
I'm
All right,
clicking
so
away as fast as I can. Yeah.
Our next speaker is Ben Monpetit. He's an associate professor here in the Department of Viticulture and Enology. And he'll be talking about gene expression profiling provides a genetic signature of vineyard site with insight into wine fermentation outcomes.
Yeah,
Take it away,
thank
Ben.
you, Karen. I'm just going to make my laser pointer hopefully a little bit more visible to everyone. Please let me know if volume or anything is problematic. So generally, upon joining the department, kind of my interests lie in the fact that I'm a yeast biologist and thinking about what the yeast are responding to within the fermentation environment and why we get diverse fermentation outcomes. So we obviously know of many factors that are important to wine fermentations and for yeast physiology and growth related to nitrogen, sugars, etc. But there are likely many other key factors that are impacting fermentation outcomes, yet we're, it's kind of not at the same level of understanding. So we wanted to ask questions about what unique factors or novel factors do we not currently consider that would be important for fermentation outcomes. So this is kind of the motivator. And when we're thinking about those factors, we're thinking about the fact that they're likely coming in the form of the grape material, and those factors are the result of all the processes that happen in the vineyard. So, how the farming is being done, obviously the variety, the rootstock, where it's being grown, et cetera, all lead to this grape material taking on a certain composition, being associated with a certain microbial community, fungal community, and this ultimately affects the fermentation through interactions with the inoculated yeast. So we're really thinking in my group a lot about what this fermentation environment is and how that affects the functions of the Saccharomyces yeast, as well as the other associated non-Saccharomyces yeast and microbial organisms that are present. So the suggestion, on our part is that, this is a very complex environment that's impacted by what goes on in the vineyard, by the associated microbiome, ultimately by the chemistry of the must and the microbial activity that can then take action. And it's through all of these kind of factors that come together that you get specific fermentation outcomes. And when I talk about fermentation outcomes, it could be many different measures. It could be the speed of the fermentation. It could be sensory aspects that result from the fermentation, et cetera. And as an industry, obviously you all very well know that different sites have different, kind of fermentation outcomes with respect to many of those parameters I just mentioned. So when I joined the department, I saw an opportunity to start to address these questions in the fact that Ron Runebaum's group at UC Davis at the time was running Pinot Noir fermentations within the teaching and research winery, where they were taking grapes from approximately 15 vineyards in Oregon and California and performing highly controlled fermentations in the winery. and doing this over multiple vintages. So we had the opportunity to sample these fermentations and think about and test, for factors that might be important for fermentation outcomes. On the right here, you can see data from 2017 and 2019 that outline the 60 fermentations basically that went for those two vintages. The 60 fermentations come from the fact that we have 15 sites and each fermentation is done in quadruplicate. As I mentioned, these are Pinot Noir fermentations. They're inoculated with RC212, and every fermentation each year is conducted in the identical way to control for those variables of winemaker and winemaking kind of protocols. And what my lab considered as part of those fermentations was what microbiome was present in the must. This is work that was also supported by Dario Cantu's lab and Carrie Steenworth's lab with Ron Runenbaum's lab as well. And then in my group, we really considered what kind of microbial activities were occurring in those musts. And we have tools where we're able to measure those activities in terms of what activities the yeast are doing through the genes or the proteins they're expressing. And we're able to actually quantify this activity for both the native fungi that are present as well as the inoculated yeast strain. So when we're analyzing this data that I'm going to share with you, I kind of refer to this as the genetic signature of site. So all of this microbial information as far as what microbes are present and what their activity is relates to measuring DNA signatures and other things. So we, again, refer to this as genetic signature of each site that we monitored. So one of the first things we asked of this data was whether there is information present within this genetic data, this genetic signature of site, that could tell us something about the sites and whether we could actually predict which site or AVA the fermentations came from. And I don't have a lot of time, obviously, to go into great detail about how you do this, but ultimately, we are able to achieve about 92% accuracy when predicting AVA. So what I mean by that is that you can select a fermentation from one of these sites. We're blinded to what that information, what that site is, and then using the data we've collected, predict where what AVA it came from. And again, we're 92% accurate in that. When we considered vineyard, we're about 70% accurate in predicting vineyard. And the loss of accuracy here was really the result of three different within what we call within AVA errors, where we would misclassify two vineyards that were relatively close together. So whether it was in the Willamette Valley, where there's two vineyards about 20 miles apart, or in the Santa Maria Valley or Arroyo Seco, where the vineyards are much, much closer. So these within AVA classification errors are not surprising. Likely these vineyards have very similar, kind of factors associated with them that would give rise to microbiomes and yeast activities that are more similar. So one thing that this data tells us is that there is information within this data we're collecting that tells us something about these sites. So this motivated further work to start to think about what that information is and what that information is telling us about these vineyard sites. Whoops. And the way we thought to go after this problem was actually by, again, using the microbes that are there and how they're responding in these fermentation environments. So, here I've kind of put it as that microbes themselves are very sophisticated sensors that we can use to determine what's going on. So Saccharomyces cerevisiae pays very close attention to the environment, what nutrients and metabolites and stressors might be in its environment, and changes its metabolism in response to that. We also have a large body of literature that indicates that Saccharomyces pays attention to who else is around in a fermentation, and there are interspecies interactions between different species of yeast, or even yeast and bacteria as well, that can lead to behavioral changes as far as what metabolism is going on and how the yeast are growing and fermenting. So they sense their environment, and this is another way of kind of graphically showing this. These microbes, and here the microbes just represented by this gray box, is sensing its environment, taking that information and responding, and the response is in line with what it's sensing. And that response is, again, in the terms of what genes or proteins are being turned on and off within the organism. And this is what we're able to read out. So our idea was that by measuring these responses, we could infer what the organism was sensing originally. So I want to give just, kind of an example of this. And what you're seeing here are, two theoretical fermentations. Imagine in fermentation 1, we measure gene expression, which is, again, a measure of activity that's going on. And maybe in this fermentation, we see something like a number of genes related to sulfur stress and some genes related to mannitol metabolism. So this tells us something about this fermentation, because we assume that if the yeast is expressing these genes related to sulfur stress, that they must be experiencing something related to sulfur stress. Same with mannitol metabolism. And maybe in fermentation 2, we see different sets of genes. We see something related to thymine metabolism and glycerol production. And again, we can make inferences about what's going on within the fermentation with respect to thymine, or why the cells might be producing glycerol. And the reason we can do this in part is that for over 90% of the genes that are expressed in Saccharomyces, we know a function for those genes. So there's about 6,000 genes in yeast, and for the vast majority of those, we have functional descriptions such as this. So what we did was we measured this activity across fermentations, replicate fermentations. We did this for all 15 sites across 2 vintages and for all 6,000 genes. For those of you that are mathematically oriented, if you quickly multiply these things together, the answer is it's a lot of data. And we had to come up with some method of interrogating this data. And that was the job of a very talented, at the time, PhD student in my group, Taylor Ryder, who as a data scientist was able to take this data and make heads and tails of it. And she's now graduated, but without her, this would have not been possible. And what she was able to do was to take information basically across all the sites and across all 6,000 genes. I'm obviously, for presentation purposes, not showing you 6,000 columns, but she takes all of that information about what genes were on or off in these different environments. And she uses a data analysis method where she's able to collapse all that data into a single data point and plot it on a graph like this. We refer to these as diffusion components. And again, for brevity purposes, I'm not going to go into what this is. And honestly, Taylor would probably do a much better job explaining it than I could. But nonetheless, what's important about these graphs is they're positioned with respect to one another. So this green spot would represent a fermentation and what's happening with all 6,000 genes in Saccharomyces cerevisiae, for instance. And we would say, based on this plot, that this fermentation was most different from this blue fermentation here, which is at some other point on this graph. And then we would also say that these 2 fermentations are most similar to each other because they're closest together. So we can take these relationships from these data and begin to understand how the fermentations relate to each other and start to extract information from those fermentations with respect to gene expression and activity. We get many different diffusion components, so there's many different plots to look at. And here's one diffusion component 1. And what we've done here for display purposes is colored the spots by bricks to give you an indication of what's going on. So you can see here that fermentations at time points where there's high Brix values, they cluster together on this side of the diffusion component. And as Brix decreases, which goes from yellow to the dark blue-purple colors, you see these positions nicely change on the plot. And again, you see activities at the end of fermentation are all more alike because they cluster together. So this gives us confidence that the way we're analyzing our data is working. Underlying each of these spots, we can go in and look at the genes that are driving the position of these spots on this graph. And this is a very complicated, busy slide, and I'm not going to go into it very far, other than to say again, because we know about those genes and what they do within yeast, we can annotate functional information on top of those, and we know which genes are involved. And we know, for instance, in early fermentation, certain activities are happening, like amino acid metabolism, where late in fermentation, other things are going on, maybe related to carbohydrate metabolism, where the yeast are changing what sugars they're going after as glucose is depleted. So there's a tremendous amount of information from these plots, which we can then harvest and think about what's going on in these fermentations. So I want to give you just one example of this. So this is a different diffusion component I'm showing you here. Now we've colored them based on AVA. And generally what we would say is that most of the fermentations show a pattern that's similar on this diffusion component, with a few exceptions. We have the organ sites here falling out. Remember, these fermentations are done in duplicate and we haven't combined the data. So for instance, these two spots come from the same two duplicate fermentations from the same vineyard, these two spots and these two spots the same way. So we ask ourselves, what is different about these fermentations than all of these that cause them to fall out? And we go back to that scenario where we start to ask the question of what genes are expressed differently. And what we find is that what drives these spots to separate from all the other fermentations are genes related to nitrogen limitation and ammonia metabolism. So this was a little bit surprising to us, because what I haven't told you so far is that these fermentations are supplemented with nitrogen. So we do not believe they should be nitrogen limited. And these fermentations all completed, again, indicating that nitrogen limitation was not a problem. Yet when we actually look at YAN values for these fermentations, these Oregon 1-2 sites and the Russian River Valley 2 site, which are represented within this cluster, are the ones that did start with the lowest YAN values. So we find this quite interesting because, again, since all the fermentations were supplemented to at least have 250 parts per million of nitrogen, yeast assimilable nitrogen, it raises questions about whether the timing of these nitrogen additions are optimal, because if the yeast are still showing signatures of nitrogen limitation, it would suggest that there are times during the fermentation when they're still nitrogen limited. Or it makes us question the source and type of nitrogen that we're supplying to these fermentations. And both of these are questions that kind of are raised by this research and things that we could obviously pursue. Other site-specific kind of factors that came up through our data analyses, and these appeared both in the 2017 and 2019 vintages, so they repeated in multiple years. Beyond the nitrogen limitation was very specific gene expression responses that we saw occurring when we detected certain bacteria or non-Saccharomyces yeast were present and active in the fermentation. So there was this interspecies relationship that we could identify. And we also saw signatures in some of the sites related to sulfur and fluoride stress, which would be another site-specific variables that may result in different different activities of the yeast and different fermentation outcomes. So if we go back to the original kind of figure that I started with this idea that there are many, many variables related to vineyard site that ultimately modify and affect what's happening during fermentation, the data we've analyzed to date on these Pinot Noir fermentations, make suggestions that one could begin to explore around, possibly the use of certain fertilizers or pesticides in the vineyard that may result in sulfur stress or fluoride stress during a fermentation, and could raise, kind of experiments and studies around the type of nutrients that are being added. And again, our work is pointing to the possibility of changing what nitrogen or the source types of nitrogen that are, or the timing of nitrogen addition with respect to nutritional management during a fermentation. So as I said, there's a lot of data there to talk about, and I'll just point people to 3 recent publications that are in the process or have just come out related to this. All 3 of these publications were led by Taylor and detail the data that is evolved in the story I told today, plus some other stuff. And these are all open access publications. Anybody should be able to click on these links and see that data. So with that, I'm going to stop and answer questions, hopefully, or what I can, and respond to those questions that are in the chat. I have to point to, of course, the people that are responsible for the work. Taylor was, as I said, the data scientist who really allowed us to assess those millions of pieces of data. Rachel in my group was key to a lot of the data or sample collection and fermentations going on in the winery. And of course, our collaborator, Ron, who established the Pinot project, and our funders. And in terms of this project, I have to point to Jackson family, who were major supporters of this, as well as Lalaman. All right, thank you for your time. And I will stop sharing so that I can see what else is going on out there.
So you do have a couple of questions in the Q&A. And the first question you got was slightly revised as I think you gave your talk. So if the AVA can be predicted more accurately than vineyard, where does farming, you mentioned, come in? Seems site trumps culture. And they said region, not site, I suppose, I think. So where does, I guess, does region trump culture or something?
Yeah, so I think the reason that AVA can be predicted more accurately than vineyard is we just in part expect that as you move more distant from each other, the differences become more obvious, and therefore the data signatures that we see are stronger. So we're able to predict them more accurately. Of course, all this data too that we're talking about is related to Pinot Noir, done with RC212 as a yeast strain, and the signals we're seeing, the responses we're seeing, may change by variety, may change based on the inoculated strain. So I didn't mention it at the end, but we are interested in kind of extending this to other varieties as well. You could think Chardonnay or something, for example, to see how this information can help us understand the differences as well between these different varieties.
There's another question. Would you expect the soil microbiomes to correspond to the microbiome in grapes and musts? Might this provide the link between microbiome, must, and AVA?
So the environment's a soil environment versus, let's say, a must environment, very different places with different selection pressures on the microbes for, who can survive and grow in those different environments. So I don't necessarily expect that there is the exact same organisms there. But clearly what's going on in the soil is going to impact what the plant is doing, and that's going to impact what is in the berries. And then of course, what's growing on the berries themselves and what comes into the winery is going to ultimately impact what's going on in the fermentation as well. And I mentioned some of those connections on the final slide there, as we see these strong connections between certain microbes and our fermentation outcomes. And one of them was a lactic acid bacteria that we see a signature for, which is connected with spoilage in the literature. And also the other one was just with Hanseníaspora uvarum activity as a non-Saccharomyces yeast as well. So there are obviously very important connections between what microbes are in the vineyard and in the soil and what happens in the must, be that direct or through the plant itself.
And the last question here is it possible that there is signal for nitrogen limitation that is affecting cell metabolism at those sites?
Ultimately, for sure, yes. If the cell thinks that it's nitrogen limited or doesn't have the right types of nitrogen, it's going to change its metabolism, and ultimately that will affect either fermentation kinetics or what types of metabolism is happening. And as soon as the cell changes what type of metabolism is happening, you think about the impact that that might have on what metabolites are being produced. And obviously as a product that for consumers, that could in fact ultimately what sensory aspects of the wine as well. So there is going to be a very kind of connection between all of those things. And we're interested in understanding that nitrogen limitation signal because, again, I would say everything we're doing, that's the kind of royal we, because I'm not the winemaker doing this, but everything that is being done is following very standard winemaking protocols, and we're adding nitrogen in a way that we would expect is reflective of exactly what's going on in the industry. So there may be some learning there as far as, again, when to add or what to add that could help change this fermentation performance aspect, or the signals that we're seeing from these yeast.
Great. Well, thank you very much. Thank you for sharing your time, Ben.
No problem. Thank you for the opportunity. And if anyone out there has questions, I see Carolyn was nice enough to put my email address in the chat box. So please, follow up and we can discuss more.
Great. Thank you so much.
Thank you.
All right. Well, last for today, our last speaker, but certainly not least, is Andy Walker. Probably all of you know Andy. He's professor in the Department of Viticulture and Enology, and he's been here for just a few years. And actually, the title of his talk, he changed the title, is going to be 30 plus years of grape breeding and just getting started. So
if I can turn the machine on.
It's coming, yeah.
We'll get it, not to worry. Start my video. Where's that one coming from? Here we go. Okay, let's get back to the beginning. Am I shared now?
Yep. We can see your slides.
These are not moving very fast though. Let me just close it here for a second. Let's try it one more time, since we do have a couple of seconds.
Yep.
Stop share.
Yeah, sometimes it's easier to stop sharing, get to where you want to be, and then share again. It's a little wonky when you're in the Zoom.
In the Zoom, yes. I'm not going to miss the Zoom very much. If it ever goes away. I have two desktops open. There's the problem. There we go. Okay, now we're getting there. Give you a quick preview. Okay, so there we go.
Great.
Are we ready?
Absolutely. Take it away.
So 30 plus years of grape breeding and just getting started. That's the sad and tragic truth. In many ways, a good breeding program exists to build upon the next one. And I'm hoping that's what's happened here as we employ a new grape breeder. And I'm looking forward to my soon to be real retirement the next couple of months, is to sit down with the new people and really get some idea of what they would like to pursue and what we can mothball and what we can sort of tag back there. And I have every intent on working with whoever the breeder is, if they'll let me, and helping with the fun stuff. No more report writing, no more proposals, just the fun stuff. So I'll be maintaining vines and helping people learn and understand how to grow these things too, which will be fun. So big thanks to the CDFA PDQuist board, which funded all of our work on Pierce disease that I'm not going to talk very much about, which is why I put them first. But it's not last, but it's a wide-ranging project which includes PD. About half of our work includes about PD, and the rest is on rootstock. So we're going to talk about mostly rootstocks today because they're more clear avenues for the next round of breeder. So with that in mind, I'm thanking the Rootstock Improvement Commission, the California Grape Rootstock Research Foundation, the CDFA Industry Improvement Board, the California Taylor Commission, the American Vineyard Foundation, Ian J. Gallo, and the Louise Rossi Endowed Chair of Viticulture Funds. Those have all gone into all the work we've done in the lab for many years now. And the current cast of characters It's fairly stable. They've been there for a while. Samara Riaz, you've heard of it, if you've heard my talks before. She does a lot of our work on the molecular genetic component of breeding. Dan sort of coordinates all the lab, and Rong is working like mad, processing samples faster than we can, or as quickly as she can to keep up with us. And Cecilia, you've heard from just a minute ago, she's working mostly on virus tolerance and the PD resistance gene as well. Now she's branching off into the CRISPR work. Alan Tencher, my assistant breeder, who's home today, I imagine, and Nina Romero, who looks after the greenhouse and the field operations diligently. Erin Garnou, you've heard from yesterday, I guess, talking with her about her project, and so she's there as well. She's finishing up her postdoc, and then over the next little bit, and hopefully taking a new job in the East. We'll see. Carla Huerta, who's working with the citrus board now, just finished her PhD, and Leila Fayaz is in Pakistan. She just finished her PhD very recently. I'm actually getting them all through the process here, which is good. Andy Nguyen, who is just about finished, gave me his final draft of his last chapter for his dissertation. So that's pretty much done too. And Chris, we're going to get toasted and out before the start of the next academic year, which is great. And Dave Scott is finishing up his project as well. So you'll hear about most of these people and what the work they're doing. So rootstocks, let's go back to the beginning then. So it really is the beginning of great breeding in many regards, as we look for ways to address phylloxera resistance and control that problem in Europe and France primarily. 1850s, more or less, the phylloxera invaded Europe from North America. And they began working for resistance, looking for resistance, first in crosses to produce direct hybrid producers that didn't need the rootstock, and they weren't very successful at that. Most of those materials were crossed with vinifera, and vinifera, I think, probably has a susceptibility, is dominant for susceptibility of phylloxera, so it's hard to breed that out of it. It's always lurking back there. And remember, of course, when we're looking at rootstocks, people always wonder why riparian and rupestris and all these crosses, because they're the only two American species that root well. So they're sort of predestined to be involved in all the crosses for rootstocks. But they lack Lyme tolerance, and that's what brought in the Berlandieri materials over time. So that's sort of in a nutshell the history of rootstock breeding. What else were they selected for? Well, they were selected for things that pleased the nurseries, which was cane length, diameter of the canes, limited lateral production, early ripening of the canes and scions as well, adaptation to wet or cold or dry conditions as they thought about where they might use these materials in the future. And then they also looked at roof architectures to some extent. They were looking at larger diameter roots that were more plunging and root systems that were more shallow. And they selected the rootstocks in those categories more or less and moved them forwards. This sort of messy slide here really is there to point out that we're facing an amazing genetic bottleneck here with the rootstock materials. It's quite interesting. We really didn't use very different accessions of those three major species, Riparia, Rupestris, and Berlandieri, and the vast majority of the rootstocks use the same accessions. And that's a problem, right? That's a challenge to the pests, rootstock pests, phylloxera and nematodes and various problems that we can think of. That's a selective pressure on them on a relatively limited genetic background. And the opportunity for breakdown and disruption of the resistance is there. It's sort of chilling. And it's lasted now for 150 years. So the question is whether it's going to last for another 150 or whether we should rethink and maybe develop a whole broader series of stocks with more diverse genetic background. And obviously that's the answer, particularly if you're a rootstock breeder. But we need to have more choices, not fewer. I think is one of the key things. The GRN rootstocks, hopefully you've heard about by now. They've been patented for a while and been out in use. They're getting to be more broadly understood. GRN1 is the most interesting amongst them because it has by far the greatest resistance. That's coming from rotundifolia, which makes it a very unusual plant and difficult to grow occasionally because of the rotundifolia component, difficult to root because of that component, but exceptional in terms of its resistance. It's also one of those odd plants that seems to devigorate. And we're always talking about how we like a devigorating rootstock. Well, here's one, and now people are confused. It's devigorating. They say maybe you should be moving your vines closer together, and you should be working with it on sort of a different mindset. The rest of the materials fall back on crosses that Leiter made back in the 60s, the foundation of that resistance, with various forms of Champinii. Rufetosa was added later, and you can see I've added more Riparia in those crosses oftentimes to try to improve rootability. So in general, these stocks do fine. The GRN5 has been hard to root and propagate, but then again, it's different genetically too. So it provides a broader source of resistance that might be important to keep around. And the other ones fall into those following categories. So remember, these have been tested for 3 strains of root knot nematode, 2 very aggressive ones that feed on harmony and freedom, and 1 more general one. They've been tested against Zyphenium index. They've been tested against all those nematodes combined together in a single inoculum, and they've been tested at high soil temperature. And that's important to remember. At high soil temperature, resistance to root knot nematodes breaks down oftentimes, and in many crop species, not just grape, cotton, tomato, a lot of different backgrounds. In addition to those resistances, the best of these materials were also tested against citrus nematode, ring nematode, a very important source of replant problems that we see around the state, for phylloxera and for lesion and pin nematodes. And MR is medium resistant, MS is medium susceptible, and R is resistant, and S is susceptible, of course, as well. So as you're going through that table, you can think about those. The big question about a lot of these is how they would do against fan leaf, and they have very good Zyphenium index resistance, all of them, but we're not sure that they prevent the dagger nematode from feeding on the root tips and vectoring the virus, or whether the resistance is lesser than that, and whether that would make any difference. And I'll go into that here in a second as we go along. So we had 2 good trials out in the state that have been pretty illustrative, and we've had it out for 10 years now. A trial in Ocampo and a trial in Geyserville. The one in the Geyserville is with Rhonda Smith, and she's doing most of the data assessment analysis of that. And Keith Stricker has been gathering data from the Gallo trial in Ocampo. So we've been slowly bringing these together, and the publication is forthcoming, which is nice. That's part of Andy Nguyen's work. Again, GRN1 from sort of these are vignettes of what we found out and what we've learned, what may be beneficial from these materials. The GRN1 is low vigor and high fruitful. It has high fruitfulness and low vigor. It's one of those magic plants that normally when we have low vigor rootstock, we have low production at the same time, and vice versa. And in this case, we see a different case. Sometimes that vigor is disconcerting because people will stretch these things too far apart. They put them on 7 and 8 foot spacings occasionally, and they don't really fill a trellis that effectively, those distances. The RS3 and RS9 are in there to compare to 2 other stocks with good dagger nematode resistance and good root knot resistance, but they've not been very good in these 2 trials. Though the Ocampo site is a deep, fertile, loamy soil, and the plants are weak there, and the Geyserville site is very gravelly and rocky, where we'd expect them to be weak, and lo and behold, they are weak there as well. But we're at the point now in the trials where we're really starting to see the impact of those pest pressures that were present when we planted. So the weaker stocks, the stocks with more moderate resistance, aren't necessarily holding up in those sites. This is an interesting bit of data that Andy Nguyen just put together. It's showing you the movement of virus into these plots, and this is from the Ocampo site. We have in that site a St. George vine as a sentinel between each of the replicates, 5 vine replicates, and we have it in there as a control in the rest of them as well. And so if we look at the St. George values, that's 35% now, them are negative of the plants we put in there. And I think there are about 60 total of the St. George. Marginally infected, 10% more or less, moderately infected, 15% more or less, and highly infected, 35%. So that's a high number, and it's equivalent to the same infection level in 1103 Paulson's. So here we have a stock that's neither stock is known for its fan leaf resistance. Of course, they're quite susceptible to nematode feeding as well. And we use those as sentinels to know where the virus is moving in the plot, and if it's uniformly spread, and whether or not we can expect to have good results. And the nice thing about this plot is it shows you that the GRN materials, all of them, are suppressing the portion of highly infected plants. But the GRN1 and the O3916 are the best at that, where they really have very few positive plants at this point. Most of them are negative, and none that are highly infected. That's good and bad. It says there's something going on here. But the bad news may be that they're going to break down soon. Just had a chance to get to this point, and they're going to get on from there. And when we released O3916 back in the mid, I guess it was the early 90s, when we released that rootstock, In those field trials that it was tested in, it took about 10 or 15 years before we started to see infection. The unique thing was that after that point, we never saw disease in those plants. We saw virus infection and clear evidence of it, but we didn't see, not in terms of ELISA testing, but we didn't see impacts on the fruit set at all. And here we're starting to see impact on the fruit, but not in the GRN1 nor in the O3916 at this point. So there's some promise that they or some indication they have some promise for a longer time period. So we're looking for that tolerance. Remember, O3916 became infected, but never showed disease. It's tolerating the presence of fan leaf in the scion, on the scion variety above. They all have excellent nematode resistance in terms of dagger and root knot, and they have good resistance against other nematodes as well. But in general, we need to look sort of beyond that. I think the rotundifolia has been the only source of resistance to or tolerance to the virus that we've seen over time. GRN2, 3, and 4 propagate beautifully and very easy to work with, have good broad nematode resistance, probably not any fan leaf resistance. And we've seen this again where plants with strong Stiphanema resistance, dagger nematode resistance really haven't had good virus resistance at all. GRN1 and 5 are a bit tricky to propagate. It's mostly because they're a bit more southerly in terms of their presence, and that's something I'll try to remember to talk about here in a second too. That changes the way those plants grow. They're not a northern species like Riparia, and even Rupestris for that matter, are more northerly and more cold hardy. And these plants are a little less cold hardy and are more central Texas and south. So it's been an issue, I think, over time. With GRN1 though, with some patience and some mature wood, they do beautifully. The trick is getting the wood to mature because it's from rotundifolia and it's a more tropical species. So what are our overall objectives? We want to now continue on. These are sort of things for the next rootstock breeder or the next breeder, whatever they choose to approach it first. But I'll sit down with them and go through this list and try to maintain stuff and direct them in the correct path to utilize these for good intent. So we need to add salt and drought resistance. You heard a bit of that from Chris earlier on. To the GRN stocks, they're not salt tolerant and they're not necessarily drought tolerant either. They haven't had really good deep root system profiles oftentimes. They seem to perform but sort of moderately, more like 1103 Paulson, which is again in that sort of moderate category too. We'd like to add some ring nematode resistance, and we've been working on that. It won't be possible to add it to GRN1 because that resistance comes from rotundifolia mostly. In fact, almost all the sources of resistance are rotundifolia based, and the hybrids with rotundifolia are sterile, so we can't really. We have to make a good, well considered cross to begin with at the F1 level, and then move forward from there. And we can't move forward with back crossing into rotundifolia and not. One of the things Olmo told me as he passed me along into this position if you make 200,000 crosses, you may find one plant with some fertility between rotundifolia and other Vitis species. That's a lot of crosses. We've probably made half of those already, but we've not detected in any case fertility with rotundifolia yet. And Olmo had found some, and he found it unfortunately in many ways in vinifera rotundifolia. So we've always questioned whether those would have decreased resistance to phlox and various other pests as well. We want to add some virus tolerance, and we'll talk a bit more about that here in a second to the overall milieu of things we'd like to produce. We've been developing lots of markers for various traits that allows us to combine and stack these things together. We're now using primarily campus-based rootstock trials to get a good feeling for these vines' performance to begin with, and that's something we hadn't done with the original stocks, and we're at that point now with the last set of materials we're putting through FPS. We'll have good yield, pruning weight, and phenological information on them before we let them loose. And we're still put out field trials, and it's still the last arbitrator of things we need to do, and we get them on a pre-release basis to FPS, where now we have somewhere around 10 different accessions that are past this session or all at the later stages of this process for release as rootstocks too. Most of those being salt. As most of you know, I've been collecting grapes for a long time. That's one of my summer adventures I take each year. And wander around mostly the southwestern United States looking for new materials. And a lot of these things have tremendous value and potential value. And we have a collection of about 1,000 of them now. They've been genetically characterized. We've done a lot of salt testing. We've done a lot of root testing on them. We've done some PD testing on them. And they have good resistance to Pierce disease, sisyphoneme index to salt in many spots. And you can see where they're growing through these more desert-like regions of both Mexico and US. So these have a lot of value. A lot of students have been sort of trained on them. I think the students start off the first day thinking, "Oh, this will be a fun time to spend some time with Andy and see what we can look at." And after 400 or 500 miles a day, they realize, well, maybe this won't be such a good time. Again, the goal is to collect as much material as possible, not to sightsee as we go through these things. A lot of these are very interesting. And this is a screen of salt tolerance of chloride concentration in the leaves. And it ranges from on the right from stocks like or selections like Repair Gloire that has essentially no chloride resistance at all. Ramsey, which is sort of intermediate, but on the high side in terms of accumulating. Schwarzman, a bit better. 140 Ruggieri, probably the best of the commercial materials. And then these other selections you can see. There's some Acerfolia down here at the far left end, some Tremesii, some Gerdiana. All these are southwestern desert species that again aren't known for their drought tolerance, but for their salt tolerance. And they're not really in droughty areas. Grapes don't like to grow in droughty areas most of the time. There's a couple of species that do, but not many. But they are in very alkaline and saline spots. And they look like they have some great promise, including the 9018 that Chris told you about earlier. We're continuing to look at fan leaf tolerance and what we should do next. We have a large number of materials now in crosses between 10114 and tray shed, which is a centifolia form. It's also a relative of 3916. We've been looking at bench grafted materials within that material to find out which seems to be working the best and which seems to be the most easily manipulable. And we've tested most of them for ring resistance and a lot of them for root knot resistance as well. And now we're looking at their ability to improve set. And that again is work by Andy Nguyen, just for his PhD is being finished up right now. And he's looked at a lot at percent set and crop weights and other things we can look at and evaluate. And it looks, some of the stuff looks quite promising too. I've been trying to figure out what is the basis of this 03916 induced tolerance for the last 30 plus years. And it's a little bit frustrating. And we get close to the end and then something evaporates. And right now, Aaron has been working very diligently on this and we're getting close to the end, but we can't get the testing done immediately. We're going to take a while and Aaron's looking for a new job. So hopefully we're going to keep her interest in this over time and we'll get the good analysis on what we're learning. But what we're really looking for is what metabolite or phytohormone is being moved from the root system up into the scion and is compensating for the impact of fan leaf on flowering in a scion. And that's what's occurring here. We want to know what that is. So we can more effectively screen for it and we can more effectively manipulate it and we can more effectively work with it from both a CRISPR perspective and from a classical breeding perspective over time. This shows you the range of concentration of fan leaf in the roots of different seedlings within these populations here, the Rotundifolia 101 population. People often ask, why is 10114 in these crosses all the time? I thought you didn't like it because it's salt tolerance or drought tolerance was poor or whatever. Well, it's a female, and we're limited, remember, in the wild species crosses because the vines are either male or female, and we need to choose the females that would root well and would be easy to pollinate and cross with, and that's what we've done here. The crosses of Rotundifolia are also very difficult because they bloom 4 to 6 weeks later than many of the Vitis species. The earliest ones would be the Riparia and some of the Rupestris and the Acerfolia for that matter are very, very early and sometimes even 2 months earlier than the Rotundifolia bloom. So making the crosses, physically making them, it can be tricky too, particularly when the early species is the female because you need that pollen from another source on it at that point. So here we have 03916 at the far side. Way at the end here, we have a couple other things that are equivalent to it. We have 10114 unaffected to show you the level, essentially non-detectable, of course. And then we have a lot of stuff that's quite interesting. And there's more of that material too. That's that definitely is suppressing the concentration of fan leaf in the root systems. We did an examination of a lot of these materials by grafting them onto both healthy and infected St. George. So we wanted to put infected material on top, of these rootstock selections at that point, to see what would happen. When we take a healthy St. George without any problems, and we graft Cabernet on top, and we look at the effect of course, healthy. There's no problems there. We have 157 berries. We have a normal number of Calyptra. We have normal fruit set, which is around 50% for these materials too. But if we take the infected one, the number of berries drops pretty radically. You can see the flowering wasn't affected much, the number of flowers, but the set is the thing that's being impacted. And we have 4% fruit set, so pretty poor and very typical. And we have healthy and infected on 03916 are the two rows below. And again, very little impact. That's why we say when we look with 03916, it both suppresses the virus presence and it suppresses the impact of the virus on set, which is what we're looking for. And if you look at the other four below it, they're doing that same thing. There's some variation there, but we can select individuals from that group that are definitely keeping high fruit set and keeping high berry number and not being impacted by the disease. So this is promising. What's the bad news then? The bad news is they're hard to propagate. And we've had to go through and very, very carefully select out materials that root better and perform better. The typical breeding approach would be then to take these individuals and graft them to something that roots better. But we can't do that because these individuals are sterile, right? They're a cross between rotundifolia and vitis, and they don't function genetically. This information here just shows you that we do have some good things. We have things that root, and we've gone through and tested them 2 or 3 times. We have things that maintain the fruit set here as well. And they're in trials now on campus out in the blocks, and they're growing well so far, and they look promising. The question is, when will we release these? They've been out there for a couple of years now, so they really haven't started fruiting from a field trial perspective yet. This other data was from earlier tests on individuals and the replicas of those individuals. But now we're moving towards something that's more field-based or viticulturally based, and we'll see how these function. We're looking at their virus tolerance too. So that's tolerance to virus, to fan leaf. And we've also observed tolerance to leaf roll and the leaf roll complexes as well. This is Deborah Galino out looking at a trial that she put together, where there's 3 replicates of the given rootstocks grafted with different strains of viruses. And we're learning more about these strains of viruses since this picture was taken and how they function. But the rootstocks behave differently. So with 5C, there's really no impact of this virus strain, which turned out to be a complex of strains. There's no impact of the virus on the health of those plants on 5C. If you put them on 5BB, that's that 3 little plants stuck between the 2 little groups of healthy plants. They're dramatically affected. In fact, it'll kill that union usually in year 3 or 4. And if you put them on freedom, they don't establish. So there's a blank image there. So we know that there's a wide variance. We've been trying to figure out a way to look at this more rapidly within a year or less if we could. I have a couple of students who've worked on this over the last few years. We know that it's variety specific, this ability to induce this grafting compatibility. And we know we have some species, some rootstocks that don't respond. And one, curiously, is AXR1. It's quite tolerant of viruses. So the other one is St. George, also very tolerant of leaf roll viruses. They become infected, but they don't become highly symptomatic. So there'll be some impact on color and maturity levels and overall vigor and health, but nowhere near what you'd expect with the very sensitive ones. And that's what Bee Freedom, 339C, 110, 5BB are very sensitive and very reactive in those cases. So we want to figure out how to screen for these quickly and how to get them moved into the program quickly, because we're getting more and more viruses, not fewer and fewer. And it's becoming to the point where people are very frustrated. So it'd be nice to have a rootstock you could graft onto that wouldn't react as aggressively to these viruses and new virus strains that are coming through. So we've made a lot of combinations with those 2 susceptible and two more tolerant combinations. And we've looked at them in different environments, both at the field level and in the greenhouse level, at multiple ways of graft inoculating these things as well. And now we've looked at them through micrografting, and we're hoping that's going to work well. And this was work that Shenhua Kui was working on here with me and Nihal Buskin, and they've both gone back to their respective countries without finishing the project when their time ran out. And we're trying to finish this up at distance, but it'll be a project that the new breeder will have to work on too, I think. Hopefully they'll decide to. I have a couple of pictures of the PD work, and I'm just going to sum it all up in 2. We've released now 5 new varieties. They're highly resistant to Pierce disease. they actually have remarkable quality. And this is a picture of Paul Skinner and Chuck Camus, Chuck Wagner, who are looking at one of their plots they have along the Napa River in St. Helena. No signs of PD. This was a terrible hotspot for a long time. And the fruit and the production is quite good. And we've been making commercial scale wines now from these for a couple of years, 3 years. Chuck's been very, very helpful with this whole process. Here's Jonathan Tomac down in Ojai and his Ambulo Blanc, which is one of our 2 whites that we released. Again, a site here that really almost destroyed him mentally because he couldn't plant grapes here. He had all this property, he wanted to put a vineyard in, and it continually died over and over and over again. The last iteration was about 8 years ago, and now the vines look great. The wines are quite nice as well. They're really coming out very well. We did a tasting at the Unified last year where we did a virtual long at distance tasting, and it was a little bit peculiar, but I think it was the response was pretty good. And we're thinking about other sorts of ways of getting more of these tasted more rapidly too. That they're similar to that. Okay, I finished. Probably finished faster than I should have, but well, maybe not because it's hard to tell. We have another. I didn't really show you pictures at all of the other 3 new PD varieties, but we have another 10 that are coming along and another 15 or 20 that are out in the field. So the question really becomes now, how many do we need? We have 5, they all resist PD and they solve the purpose. They could be blended in, but the aspects now are thinking of these things from more varietal level. What can we do with them? Do they produce international quality wines, I guess, however you want to look at their quality components and categorization, and I think they do, and we've been noticing that, and the winemakers who have helped us with the screening and tasting trials we've gone through with these are very impressed with the potential quality. So the next hurdle is, how do we get over this hump that says there's only 10 varieties that are worthy of naming and putting in bottles around the world? And of course, that's not true. We have thousands of varieties that are potential of that category, but we are winnowing down the possible plant choices over and over again. And we have enough PD resistant vines then. So if you look at that from that perspective, 5 is enough. But if you talk to a winemaker and who wants to actually use these in a broader program, he or she will tell you, no, we want all of them. We want all the possible combinations. And we've been trying to make these as diversely as possible in terms of their aromatic and flavors and characteristics in that as well. So there's lots coming on that'll be available, and we'll get them through the pipeline as people so desire. Okay, I don't see Karen jumping up and down yet, but she's probably getting a bit more agitated. Any questions?
Yeah, there are a couple of questions.
Okay.
Do you do any open source searching for new rootstock material? And then in parentheses, it's amateur/cloud searching.
I don't know. Do I search for new species next session? I'm not quite sure we're getting at with cloud species. Once again,
You'd be looking to see what else is out there.
Oh,
someone else is doing.
Well, I do a lot of driving to find out what's out there, and I
guess what people are working on.
Yeah, well, there's not many rootstock breeders in the world. There's 2 in California. There's another 3 or 4 around the planet. There's not been a lot of interest in really expanding and increasing the effort on that, which is interesting because I think it needs a lot. It needs that expansion. And we're hitting a point at which there's going to be a crisis potentially. I mean, 100 years of phlox resistance is remarkable. It's probably the most remarkable story of pest resistance that exists in terms of its durability and longevity. Normally, these resistances break down, and we constantly produce new materials to address that evolutionary process. So there's need for it without question, but there aren't a whole lot of people doing a lot of rootstock breeding yet.
And the other question is, how about mildew resistance?
We didn't talk about that, but it's coming along very well. And we've been working with 6 different genes, powdery mildew resistance genes. We've been advancing those genes through multiple generations by crossing to vinifera and then taking those hybrids and crossing to vinifera again to improve their quality. And we are pretty convinced as an international community of powdery mildew resistance geneticists that we're going to need more than one gene in one plant. We need a broader, more durable base of resistance. So we've been stacking these things together, and we've been stacking them at high percentages of vinifera. One of the problems with stacking them together, of course, is when you cross with the wild type, you're disrupting all the quality parameters of vinifera. It's broken apart through the recombination process. If we can cross with something that's already been partly improved in terms of the percentage of vinifera in it, with another material with a different line that's also been improved to the same level, we can maintain the quality of vinifera, and we can include the resistance from the wild species. And we've been doing that now for quite some time. And we have we've been bringing the mildew resistance forward in multiple backgrounds, and at the point now where we're integrating them into the one package. We've also integrated them into the PD resistance package. So we've been doing that whole same process with the same philosophy. We have 97% vinifera PD resistant material. Now we need 95, 97% powdery mildew resistant material. We cross those both together and we select from that process. And that's where we're at now. We'll be making in fact, we made the first wines last fall, and we'll be looking at those this spring. That's coming along too.
Oh, say that again.
That's coming along too. Lots of projects for the new breeder. I should probably just regenerate myself and start again.
So like when you retire, you're going to be just doing more work, right?
Well, that'd be fun work.
Well, thank you very much, Andy.
Sure. My pleasure.
We appreciate your sharing your time and all of those, all the work you've done. It's a lot.
It's been a fun time.
Hey there, Anita.
Hello. Well, we're actually 10 minutes, almost 10 minutes to 12. That is a great start. We can have lunch slightly early. Thank you for our audience. Thank you for being interested in what we're doing at UC Davis and specifically at the Department of Viticulture and Enology. If you're not interested in what we're doing, why are we doing it? You're our constituents, you're the people that we're working and doing this research for, in the hope that one day you'll be able to apply this in your own operations and that it will help you be more efficient and produce a good sustainable product. I would like to thank all the speakers as well, faculty, researchers, and students. I need to thank Karen Block, our industry, our Director of Industry Relations. She did a lot of getting this agenda together, getting all the flash talks organized, nagging people. Caroline Furman, our program representative, doing all the registrations and all the nitty-gritty Zoom links and all the things that I would totally mess up if I had to do this. Thank you to our extension partners again. Without their support, it would be so much more difficult for us to do the amount of extension and industry connection that we are able to do. It will be 2 years from now before we have our next RAVE, and that will be in person. That will be in person. Our next program is for the 12th and 13th of May. You will see an email about that shortly. It is a program focused on viticulture, organized by Khan Cottrell, specifically on canopy management. And we'll keep you up to date with any future programs. We hope very soon, definitely, hopefully in the later part of the year, we will be able to do some in-person workshops and seminars. We can't wait to see you all in person and do some real networking. That's the one thing that I really miss with these virtual programs. But it's nice to see your names and faces sometimes over Zoom. Thank you very much. Thank you for being with us today and hope to see you soon. Goodbye.
Bye.